If you like the space and learn about its curiosities, consider subscribing to the channel. We have 2 videos every week. Thank you for your attention and enjoy the video. The vast expanse of space has always fascinated humanity, stretching beyond our comprehension and challenging the boundaries of our imagination. It's a place where the rules we take for granted on Earth seem to dissolve, and the unknown dominates. Since the dawn of human civilization, people have gazed up at the night sky, weaving myths and stories about the stars. But as we've grown more knowledgeable, we've uncovered truths about space that are far more bizarre than anything we could have ever imagined. Let's embark on a journey through some of the most fascinating and strange curiosities that the universe has to offer. When you look up at the stars, you're seeing into the past. The light from those stars takes millions, even billions, of years to reach us. In a sense, we are observing a snapshot of the universe as it was long ago. The nearest star to Earth, Proxima Centauri, is over 4 light years away, meaning its light takes more than 4 years to arrive. This time lag becomes even more mind-boggling when we look at distant galaxies, some of which we see as they were when dinosaurs roamed the Earth. In space, time and gravity play tricks on each other. The phenomenon of time dilation means that time can move at different speeds depending on your proximity to strong gravitational fields. For example, if you were to orbit a black hole, time would pass slower for you relative to someone far away from it. This isn't just a theoretical concept. It's something that's been proven through experiments. On the International Space Station, astronauts actually age a tiny bit slower than people on Earth because they are moving at high speeds and are farther from Earth's gravitational pull. Speaking of black holes, these enigmatic objects are some of the most mysterious in the universe. Black holes form when massive stars collapse under their own gravity, compressing matter into an infinitely dense point called a singularity. The gravitational pull of a black hole is so strong that not even light can escape from it, hence the name black hole. But the strangest part is what happens near the event horizon, the point of no return. If you were to fall into a black hole, from your perspective, you might not notice anything unusual as you cross the event horizon. But to an outside observer, you would appear to freeze in time, slowly fading from view as the black hole's gravity distorts light. Moving away from these dark mysteries, we find equally puzzling phenomena in the form of neutron stars. These are the remnants of supernova explosions, where the core of a star collapses and compresses to an incredibly small size, packing more mass than the sun into a sphere just a few kilometers wide. A sugar cube-sized amount of neutron star material would weigh more than 1 billion tons on Earth. Neutron stars also have incredibly strong magnetic fields, and some rotate at astonishing speeds. These spinning neutron stars are known as pulsars, and they emit beams of electromagnetic radiation, which sweep across space like cosmic lighthouses. Cosmic phenomena aren't just about violent collapses or extreme gravity. Take, for instance, the concept of cosmic microwave background radiation. This faint glow of radiation fills the universe and is considered one of the strongest pieces of evidence for the Big Bang. It's the afterglow of the early universe, a remnant from a time when the cosmos was just 380,000 years old. Before that, the universe was so hot and dense that atoms couldn't form, and light couldn't travel through space. But as it expanded and cooled, atoms began to form, allowing light to shine across the cosmos for the first time. That light, stretched and redshifted over billions of years, is what we now detect as the cosmic microwave background. We can't explore space curiosities without mentioning the bizarre nature of exoplanets, planets that orbit stars outside our solar system. Over the past few decades, astronomers have discovered thousands of these worlds, many of which defy our understanding of planetary science. For instance, there are hot Jupiters, gas giants that orbit extremely close to their stars, so close that their atmospheres are being stripped away by stellar winds. There are also planets that are entirely made of diamond, like 55 Cancri, which is believed to have a carbon-rich composition. Then there are rogue planets, worlds that wander the galaxy, not bound to any star, drifting in the dark void between solar systems. While exoplanets capture our imaginations, there are still plenty of mysteries in our own solar system. Take Saturn's moon, Titan. Titan is the only moon in the solar system with a thick atmosphere, and it's the only place besides Earth where stable bodies of liquid have been found on the surface. However, unlike Earth's rivers and lakes, Titans are made of methane and ethane. On this distant moon, it rains hydrocarbons, and vast seas of methane stretch out under orange skies. Mars, too, continues to intrigue scientists and the public alike. It's a planet that has been dry and barren for millions of years, but evidence suggests that it once had liquid water flowing across its surface. Ancient river valleys and lake beds hint at a time when Mars had a much thicker atmosphere, and possibly even life. NASA's rovers continue to explore the Martian landscape, searching for signs of past life, and perhaps in the near future, human footprints will join their tracks in the red dust. Even closer to home, the moon holds its own secrets. The far side of the moon, often called the dark side, is a place that humans have never directly explored. It's not actually dark, it gets just as much sunlight as the near side, but it's completely different in terms of its geological features. The far side is much rougher, with more craters and fewer flat seas of lava. Why the two sides are so different is still a mystery. Comets, too, are relics from the early solar system, made of ice, dust, and rock. These ancient travelers come from the distant edges of the solar system, from regions like the Oort cloud, and when they approach the sun, their ice begins to vaporize, creating the glowing coma and long tail that we associate with them. But comets also hold clues to the origins of life on Earth. Some scientists believe that comets may have delivered water and organic molecules to our planet in its early history, possibly jump-starting the process of life. As we delve deeper into the mysteries of space, we encounter phenomena that challenge our understanding of physics itself. Take dark matter, for example. This invisible substance makes up about 85% of the matter in the universe, yet we have never detected it directly. We know it exists because of the way it affects the motion of galaxies and the bending of light through gravitational lensing, but its true nature remains elusive. Similarly, dark energy, which makes up around 70% of the universe's energy density, is even more mysterious. It's thought to be responsible for the accelerating expansion of the universe, but beyond that, we know almost nothing about it. Then there's the concept of parallel universes. Some theories in quantum mechanics and cosmology suggest that our universe might be just one of many, each with its own laws of physics. This idea is known as the multiverse, and while it's still highly speculative, it opens up the possibility of infinite variations of reality. Somewhere out there, in one of these parallel universes, there might be a version of Earth where everything is slightly different, where history took a different course, or where the laws of physics themselves are unrecognizable. The deeper we look into space, the more we realize just how much we don't know. Space is a place of contradictions, where extreme violence and serene beauty exist side by side. It's a place that defies our understanding of time, matter, and energy. And yet, it's also a place that beckons us to explore, to push the limits of our knowledge, and to ponder the big questions about our place in the universe. What we've discovered so far is just the tip of the cosmic iceberg, and as our technology advances, we're bound to uncover even more wonders in the vast, uncharted territories of space. As we continue to explore the cosmos, one thing becomes clear. Space is not just a frontier of science and technology, but a frontier of human curiosity and imagination. The more we learn, the more questions we have. And with each new discovery, we inch closer to understanding the true nature of the universe. A place far stranger, more beautiful, and more complex than we could have ever dreamed. The more we peer into the cosmos, the more our sense of wonder deepens. Each new discovery, each unexplainable phenomenon, stretches the limits of our understanding. One of the strangest and most intriguing questions that astronomers and physicists grapple with is the possibility of life elsewhere in the universe. For decades, we have searched for signs of extraterrestrial life, whether it's microbial life on Mars or signals from distant civilizations. And while we have yet to find definitive evidence, the conditions for life may exist in far more places than we once thought. The search for life beyond Earth has taken on new dimensions with the discovery of extremophiles, organisms on Earth that thrive in the most hostile environments imaginable. These life forms are found in places that were once thought to be completely inhospitable, like deep-sea hydrothermal vents, acidic lakes, or beneath glaciers. Their existence has led scientists to speculate that life might exist in similarly extreme environments elsewhere in the solar system, such as beneath the icy crusts of moons like Europa and Enceladus. These moons are believed to harbor vast oceans of liquid water beneath their frozen surfaces, kept warm by the gravitational interactions with their host planets. Could these hidden oceans be teeming with life, just as Earth's deep oceans are? Europa, one of Jupiter's moons, has long fascinated scientists due to its potential to support life. Its icy shell, several kilometers thick, conceals a vast, salty ocean beneath. This ocean is thought to be in contact with Europa's rocky mantle, creating the perfect environment for chemical reactions similar to those that might have given rise to life on Earth. Missions to explore Europa's surface, such as NASA's upcoming Europa Clipper, aim to determine whether this moon might indeed be one of the best candidates for extraterrestrial life in our solar system. Similarly, Saturn's moon Enceladus, once thought to be a cold, lifeless world, shocked scientists when geysers of water vapor were discovered erupting from its south pole. These plumes are believed to originate from an ocean beneath the moon's icy crust, and they contain organic molecules, key ingredients for life. This discovery has made Enceladus another prime candidate in the search for alien life, particularly since the geysers shoot material directly into space, where it can be easily analyzed by passing spacecraft. While these moons might harbor the potential for life, the search for extraterrestrial intelligence, SETI, is an entirely different pursuit. For decades, scientists have scanned the skies for radio signals or other signs of intelligent civilizations. Despite the vastness of space, the famous WOW signal, detected in 1977, remains one of the most tantalizing, unexplained events. This short-lived, strong radio signal, detected by a SETI researcher, has never been observed again, leading to speculation about whether it was a fleeting signal from an extraterrestrial source or simply a natural cosmic event. The discovery of exoplanets has also transformed our understanding of how common planets are in the universe. When the first exoplanet was discovered in 1992, no one could have predicted just how many would soon be found. Thanks to missions like the Kepler Space Telescope, we now know that planets are incredibly common. Most stars in the Milky Way likely have at least one planet orbiting them. Some of these exoplanets lie in the so-called habitable zone of their stars, where conditions might be just right for liquid water to exist. These Goldilocks planets are prime targets in the search for life beyond Earth. But life might not look anything like what we expect. On Earth, all known life is carbon-based and relies on water. However, it's possible that life elsewhere in the universe could be based on entirely different chemistry. Some scientists speculate that silicon-based life forms could exist in environments vastly different from our own. Others propose that life might thrive in conditions where liquid methane, rather than water, is the primary solvent, as might be the case on Titan, Saturn's largest moon. As we ponder the potential for life elsewhere, we also face the question of how long civilizations might last. The Drake equation, a formula developed in the 1960s by astrophysicist Frank Drake, attempts to estimate the number of advanced civilizations in our galaxy. One of the key factors in the equation is the lifespan of a technologically advanced civilization. If civilizations tend to self-destruct shortly after developing advanced technologies, through war, environmental collapse, or other disasters, the chances of finding another civilization at the same time as ours may be incredibly low. This idea, known as the Great Filter, suggests that while life might be common, intelligent life capable of communication might be exceedingly rare. On a grander scale, the sheer size of the universe raises questions about whether we could ever realistically communicate with distant civilizations. Even if we were to detect a signal from another intelligent species, the vast distances involved would mean that by the time we receive the signal, that civilization might no longer exist. The speed of light, while fast by our standards, is still a limiting factor in the vast reaches of space. It takes over 4 years for light from our nearest star, Proxima Centauri, to reach Earth. For more distant stars, the travel time for signals could span thousands or even millions of years. The Fermi paradox highlights another layer of complexity in the search for extraterrestrial intelligence. Named after physicist Enrico Fermi, the paradox questions why, given the vast number of stars and planets in the galaxy, we have not yet encountered any signs of intelligent life. With so many potentially habitable worlds, why is the universe seemingly silent? There are many potential explanations for this, ranging from the idea that intelligent life is incredibly rare to the possibility that advanced civilizations are intentionally avoiding us, or that they are communicating in ways that we are not yet capable of detecting. One potential solution to the Fermi paradox is the idea that intelligent life might be so advanced that it no longer needs to use physical forms or conventional technology. Some speculate that advanced civilizations might have transitioned into digital or post-biological states, uploading their consciousness into vast, energy-efficient networks that we would have no way of detecting. This raises the question of what the ultimate fate of intelligent life might be. Does technological advancement inevitably lead to a form of existence that is beyond our current comprehension? While these speculative ideas are fascinating, they also remind us of how little we truly know about the universe. Even as we send probes to explore distant planets and moons, and as we build ever more powerful telescopes to peer deeper into space, we are still only scratching the surface of cosmic knowledge. The universe is far older and more expansive than we can easily grasp, and it operates on timescales and distances that challenge our understanding. In the end, the quest to understand space is not just about answering scientific questions. It's also about understanding our place in the cosmos. Are we alone, or are we part of a vast, interconnected web of life that stretches across the stars? The answers may still be far away, but each new discovery brings us a little closer to unraveling the mysteries of the universe. And even if we never find other life, the journey of exploration itself is one of the greatest adventures humanity has ever embarked upon. What remains clear is that the more we learn about space, the more we realize how much remains unknown. The universe is full of wonders that defy our expectations, from strange new worlds to the possibility of life beyond our own. Every time we solve one cosmic mystery, countless more seem to emerge, pulling us deeper into the unknown. As our exploration of space continues, we begin to uncover some of the most peculiar and unexpected phenomena the universe has to offer. One of these extraordinary events is the existence of so-called zombie stars. These are not science fiction creations, but real, observed phenomena in the form of white dwarfs that come back to life under the right conditions. White dwarfs are the remnants of stars like our Sun that have exhausted their nuclear fuel. Typically, after shedding their outer layers, these stellar remnants slowly cool over time, fading into obscurity. However, in binary star systems, where a white dwarf orbits a companion star, things can take a dramatic turn. The white dwarf can begin to siphon material from its companion star, reigniting nuclear fusion on its surface. This explosive process leads to a nova, a sudden and powerful outburst of energy, temporarily making the white dwarf appear far brighter. In extreme cases, the white dwarf might accumulate enough mass to trigger a supernova, completely obliterating itself in the process. Equally captivating are neutron stars, especially those that manifest as magnetars. Neutron stars with magnetic fields 1,000 trillion times stronger than Earth's. Magnetars are among the most extreme objects in the universe, and their magnetic fields are so powerful that they could erase the data on a credit card from as far as 100,000 kilometers away. Occasionally, these intense magnetic fields undergo sudden shifts, releasing vast amounts of energy in the form of gamma-ray bursts. These bursts are so energetic that if one were to occur within 10 light-years of Earth, it could cause catastrophic damage to our planet's atmosphere. Thankfully, the nearest known magnetar is about 9,000 light-years away, safely beyond the range of causing us any harm. Stranger still is the phenomenon of rogue planets. Unlike the planets in our solar system, which orbit a central star, rogue planets wander through the galaxy without being tethered to any star. These planets likely formed around stars, but were later ejected from their systems due to gravitational interactions with other planets or stars. They now drift through the cold, dark expanse of space, While you might expect these lonely wanderers to be barren and frozen, some theories suggest that rogue planets could still support life. If a rogue planet has a thick atmosphere or an internal heat source, such as geothermal activity, it might be able to maintain liquid water beneath its surface, creating potential habitats for life, even in the depths of interstellar space. In addition to rogue planets, there are also rogue black holes. Black holes, typically known for lurking at the centers of galaxies or as the remnants of massive stars, can also be kicked out of their systems by violent cosmic events. These rogue black holes roam the galaxy unseen, posing an invisible danger to anything in their path. Although we have yet to detect one directly, their existence is supported by the mechanics of gravitational dynamics, and astronomers continue to search for signs of these dark, wandering giants. One of the most perplexing phenomena in modern astronomy is the existence of fast radio bursts, FRBs. These are incredibly brief but intense bursts of radio waves that originate from deep space, often lasting only a few milliseconds. The exact cause of FRBs remains a mystery, but they are believed to be the result of cataclysmic cosmic events, such as the merging of neutron stars or the collapse of massive objects. Some FRBs repeat, while others are one-time events, further adding to the enigma. Despite numerous detections, the origin and mechanism behind these bursts remain one of the most tantalizing unsolved puzzles in astrophysics. As we consider the strange and extreme, we can't ignore the most peculiar force in the universe, gravity. While gravity is a familiar force that governs the motions of objects in space, the effects it can have on the largest and smallest scales are anything but ordinary. One of the most bizarre consequences of gravity is the existence of time dilation near massive objects. According to Einstein's theory of general relativity, time passes more slowly in stronger gravitational fields. This means that if you were to stand on the surface of a neutron star or near the event horizon of a black hole, time would move at a fraction of the speed experienced by someone farther away. The extreme gravity would bend space and time to such an extent that what appears as mere seconds for you could be hours or even years for an outside observer. Another strange effect of gravity is seen in the concept of gravitational waves, ripples in the fabric of space-time caused by the acceleration of massive objects, such as merging black holes or neutron stars. These waves were first predicted by Einstein, but it wasn't until 2015 that they were directly detected by the LIGO experiment. Gravitational waves have opened up a completely new way of observing the universe, allowing us to hear the violent collisions of massive objects that were previously invisible to us through traditional methods of observation. On the largest scale, gravity plays a role in one of the biggest questions of all, the ultimate fate of the universe. For a long time, scientists debated whether the expansion of the universe would eventually slow down and reverse, leading to a big crunch where everything collapses back into a singularity. However, the discovery of dark energy in the late 1990s changed our understanding of cosmic expansion. Rather than slowing down, the universe is expanding at an accelerating rate, driven by this mysterious force. Dark energy, which makes up about 70% of the universe's total energy density, is one of the greatest unsolved mysteries in modern cosmology. We don't yet know what dark energy is or how it works, but its presence suggests that the universe might continue expanding forever, eventually becoming cold and empty in a scenario known as the Big Freeze. This expanding universe also brings us to one of the strangest and least understood concepts in modern physics, the multiverse. According to some interpretations of quantum mechanics and string theory, our universe might be just one of many, perhaps even an infinite number, that exist in parallel. Each of these universes could have its own laws of physics, its own history, and its own version of reality. While the multiverse remains a theoretical construct, it raises profound questions about the nature of existence. If there are infinite universes, does that mean there are infinite versions of ourselves, living out every possible variation of our lives? As we look further into space, we also begin to see how interconnected everything is on a cosmic scale. For instance, the elements that make up our bodies, carbon, oxygen, nitrogen, were forged in the hearts of stars. When massive stars reach the end of their lives, they explode in supernovae, scattering these elements into space, where they eventually coalesce into new stars, planets, and even life. In a very real sense, we are made of stardust. Every atom in our body was once part of a star that lived and died billions of years ago. Space also plays host to bizarre cosmic events that occur on mind-boggling timescales. One such event is the eventual fate of our own Sunday, currently a middle-aged star. The Sun will one day exhaust its supply of hydrogen fuel and enter the next phase of its life cycle. In about 5 billion years, it will swell into a red giant, engulfing the inner planets, possibly even reaching as far as Earth. After shedding its outer layers, the Sun will shrink down into a white dwarf, a dense remnant that will gradually cool over trillions of years. The remnants of the solar system will continue to drift through space, a silent reminder of the star that once shone at its center. As we contemplate these cosmic timescales, it's humbling to realize how fleeting our existence is in the grand scheme of things. The universe is billions of years old, and it will continue to evolve for billions, even trillions of years after we are gone. Yet, despite our brief moment in cosmic history, we have developed the ability to understand and explore the universe in ways that were unimaginable just a few centuries ago. This constant quest for knowledge is what drives our exploration of space. Every new discovery, no matter how small, brings us closer to understanding the true nature of the universe. From the smallest particles to the largest galaxies, from the search for extraterrestrial life to the study of dark matter and dark energy, the mysteries of space are vast and complex. And yet, with each new breakthrough, we are reminded of the incredible power of human curiosity, the same force that has driven us to explore the farthest reaches of the cosmos, and which will undoubtedly continue to push us forward into the unknown. As our journey through the cosmos continues, we encounter even more perplexing and awe-inspiring phenomena that deepen our appreciation for the sheer scale and mystery of the universe. One of the most striking examples of this is the concept of cosmic inflation. Shortly after the Big Bang, the universe underwent an unimaginably rapid expansion, growing exponentially in a fraction of a second. This theory of inflation helps explain several puzzles in cosmology, such as why the universe appears so uniform in all directions. During inflation, the fabric of space stretched so much that even regions that were once incredibly close to each other were pulled far apart. This rapid expansion smoothed out irregularities, giving us the relatively homogeneous universe we observe today. However, inflation also seeded tiny fluctuations in density, which eventually grew into the galaxies, stars, and planets we see now. Speaking of the universe's structure, another fascinating aspect of space is the cosmic web. On the largest scales, galaxies are not distributed randomly throughout the universe. Instead, they form a vast, intricate network of filaments and voids, often referred to as the cosmic web. These filaments are made of dark matter and galaxies, stretching across hundreds of millions of light years, with enormous voids, regions with very few galaxies, lying between them. This web-like structure is one of the clearest indicators of how dark matter influences the large-scale organization of the universe. Dark matter, though invisible, exerts gravitational forces that guide the formation of galaxies and galaxy clusters along these filaments. The cosmic web gives us a glimpse into the architecture of the universe, showing us how matter is distributed on the grandest scale. At the heart of many galaxies, including our own Milky Way, lies one of the most enigmatic objects in the universe, a supermassive black hole. These black holes have masses millions or even billions of times greater than the Sun, and their presence exerts a profound influence on their host galaxies. While we still don't fully understand how these gargantuan objects form, it's clear that they play a crucial role in galaxy evolution. The supermassive black hole at the center of the Milky Way, known as Sagittarius A*, has a mass equivalent to about 4 million suns. Despite its enormous size, it is relatively quiet compared to some other supermassive black holes, which can emit tremendous amounts of radiation as they devour matter from their surroundings. One of the most extreme examples of black hole activity is found in quasars, some of the brightest objects in the universe. Quasars are powered by supermassive black holes that are actively feeding on nearby gas and dust, creating massive accretion disks of swirling material. As this material spirals into the black hole, it heats up to millions of degrees, emitting dazzling amounts of light and energy. Some quasars are so bright that they outshine entire galaxies. These objects are typically found in the early universe, providing astronomers with valuable insights into the formation and evolution of galaxies during cosmic history's earliest epochs. Another strange and poorly understood aspect of the universe is the phenomenon of cosmic rays. These high-energy particles, which include protons, electrons, and atomic nuclei, travel through space at nearly the speed of light. Cosmic rays are constantly bombarding Earth, and while most are harmlessly absorbed by our atmosphere, a small percentage make it to the surface. Their origins, however, are still a matter of investigation. Some cosmic rays come from the Sun, while others are believed to originate from distant supernova explosions or other energetic events in the galaxy. The highest energy cosmic rays, however, appear to come from outside the Milky Way, possibly from active galactic nuclei, or even more exotic sources such as gamma-ray bursts. The study of cosmic rays is not only important for understanding astrophysical processes, but also for practical reasons. Cosmic rays pose a potential hazard to astronauts and spacecraft in deep space. While cosmic rays are difficult to detect, other types of messengers from space are helping scientists unlock the secrets of the universe. One of the most exciting developments in recent years has been the detection of neutrinos, nearly massless, subatomic particles that barely interact with normal matter. Neutrinos are produced in a wide variety of astrophysical processes, from nuclear reactions in the Sun to the collisions of distant galaxies. Because they interact so weakly with matter, neutrinos can travel vast distances across the universe without being absorbed or scattered. This makes them invaluable tools for studying processes that are otherwise difficult to observe. In 2017, scientists detected neutrinos originating from a distant blazar, a type of active galactic nucleus, providing new insights into the most energetic events in the cosmos. As we examine these high-energy phenomena, it's important to remember that not all of space's mysteries are found in the distant universe. Some of the most curious events take place right in our cosmic backyard. Take, for example, the Kuiper Belt, a region of the solar system beyond Neptune that is filled with icy bodies and dwarf planets. One of the most famous inhabitants of the Kuiper Belt is Pluto, which was reclassified as a dwarf planet in 2006. But Pluto is not alone. There are many other large objects in this distant region, including Eris, Haumea, and Makemake. These distant worlds are remnants from the early solar system, preserved in the cold outer reaches of the Sun's gravitational influence. The Kuiper Belt also raises intriguing questions about the possibility of a yet undiscovered planet lurking far beyond Pluto. Some astronomers have proposed the existence of Planet 9, a hypothetical planet that could be influencing the orbits of objects in the outer solar system. While no direct evidence of this planet has been found yet, its existence would help explain certain anomalies in the orbits of Kuiper Belt objects. If Planet 9 exists, it would be several times more massive than Earth and located hundreds of times farther from the Sun, making it incredibly difficult to detect with current telescopes. Closer still, the Oort cloud, a vast spherical shell of icy objects that surrounds the solar system, represents the boundary of the Sun's influence. The Oort cloud is the source of long-period comets, those with orbits that can take thousands of years to complete. These comets spend most of their time in the distant reaches of the solar system, only occasionally venturing close to the Sun. When they do, they heat up and develop the iconic tails that make comets so spectacular to observe. The study of comets provides important clues about the early solar system, as they are essentially frozen time capsules from that distant era. In addition to comets, asteroids also hold valuable information about the formation of the solar system. Most asteroids reside in the asteroid belt between Mars and Jupiter, but occasionally, asteroids stray from their orbits and come close to Earth. Some of these near-Earth asteroids pose a potential threat to our planet, and astronomers carefully track their movements to assess any possible collision risks. NASA's recent DART mission, which successfully altered the trajectory of a small asteroid by intentionally crashing a spacecraft into it, demonstrates how we might be able to defend Earth from a potential asteroid impact in the future. The study of asteroids has also led to one of the most intriguing discoveries in recent years: the detection of interstellar objects passing through our solar system. In 2017, astronomers detected Oumuamua, the first known object from outside our solar system to pass through. Unlike any asteroid or comet seen before, Oumuamua had a strange, elongated shape and exhibited unusual behavior, sparking speculation about its origins. Some even suggested it might be an alien probe, though most scientists believe it was a natural object, possibly a fragment of a distant, icy body. Just 2 years later, another interstellar object, 2I/Borisov, was discovered, confirming that such visitors are more common than previously thought. These interstellar objects provide a rare opportunity to study material from other star systems, offering tantalizing hints about what lies beyond our solar neighborhood. As we continue to study the universe, it's clear that each new discovery opens the door to even deeper mysteries. From the largest scales of cosmic structure to the tiniest subatomic particles, the universe is full of surprises that challenge our understanding of physics, chemistry, and biology. The more we learn, the more we realize how much is left to discover. Space, in all its vastness and complexity, remains the final frontier, a place where human curiosity will continue to push the boundaries of knowledge for generations to come. As we delve deeper into the wonders of the cosmos, it becomes increasingly clear that space is a domain of seemingly infinite mysteries and contradictions. One of the most captivating concepts in modern astrophysics is the idea of wormholes, theoretical passages through space-time that could potentially connect distant regions of the universe. According to Einstein's theory of general relativity, wormholes are possible solutions to the equations governing the behavior of space and time. These hypothetical tunnels could act as shortcuts, allowing for near-instantaneous travel between distant parts of the cosmos. However, while wormholes make for exciting science fiction, they remain purely theoretical at this point. If they do exist, the question of how stable or traversable they are remains a significant challenge. Any journey through a wormhole, if feasible, would likely require some form of exotic matter with negative energy density to keep the passage open, something that has not yet been observed in nature. While wormholes represent a speculative but fascinating possibility, the phenomenon of black holes is a reality, and our understanding of these strange objects continues to evolve. One of the most intriguing aspects of black holes is their connection to the concept of Hawking radiation, named after physicist Stephen Hawking, who proposed in 1974 that black holes are not entirely black. Instead, they slowly lose mass and energy through a process involving quantum effects near the event horizon. Over time, this radiation could cause black holes to evaporate, although for large black holes, this process would take longer than the current age of the universe. Hawking radiation was a groundbreaking idea because it bridged the gap between quantum mechanics and general relativity, two of the most important but seemingly incompatible theories in physics. Another mind-bending concept tied to black holes is the information paradox. According to the laws of quantum mechanics, information about the state of a physical system can never be completely lost. However, when an object falls into a black hole, it appears that all information about it is destroyed once it crosses the event horizon. This creates a paradox. Does the information simply vanish, or is it somehow preserved? Physicists have debated this question for decades, and while no definitive solution has been found, some recent theories suggest that the information might be encoded in the event horizon itself, or possibly preserved in a holographic way on the surface of the black hole. This leads to the tantalizing possibility that black holes could act as cosmic storage devices, holding the information of everything they have ever consumed, though how we might access or interpret this data remains a profound mystery. As we continue to unravel the complexities of black holes, we must also consider one of the most puzzling forces driving the evolution of the universe: dark energy. Dark energy, which makes up about 70% of the universe's total energy content, is the force responsible for the accelerated expansion of the universe. Its nature remains one of the greatest unsolved questions in cosmology. Unlike dark matter, which interacts with gravity and helps hold galaxies together, dark energy seems to work in opposition to gravity, pushing galaxies apart at an ever-increasing rate. The discovery of this accelerated expansion in the late 1990s by teams studying distant supernovae came as a shock to the scientific community, and ever since, researchers have been trying to understand the true nature of dark energy. Some theories propose that it could be a property of space itself, while others suggest it might be a new, undiscovered field permeating the universe. The implications of dark energy extend far beyond the present. If the universe continues to expand at an accelerating rate, it could lead to a scenario known as the Big Rip, where galaxies, stars, planets, and even atoms are eventually torn apart by the ever-growing force of dark energy. However, this is only one possible outcome. Another possibility is that the universe could continue expanding but at a slower rate, eventually reaching a stable state known as the heat death, where all stars burn out, and the universe becomes cold and lifeless. These scenarios, while distant, challenge us to think about the ultimate fate of the universe and our place within it. As we explore the forces shaping the universe on the largest scales, we are also uncovering extraordinary details about the smallest scales. Quantum mechanics, the branch of physics that deals with the behavior of particles at the subatomic level, has revealed a universe that is far stranger and less intuitive than we could have ever imagined. One of the most bizarre phenomena in quantum mechanics is quantum entanglement, a process in which two particles become linked in such a way that the state of one particle is instantly connected to the state of the other, no matter how far apart they are. This spooky action at a distance, as Albert Einstein famously called it, has been experimentally verified, yet it defies our classical understanding of how the universe works. Entanglement suggests that particles can communicate instantaneously, even across vast distances, which seems to violate the principle that nothing can travel faster than the speed of light. This strange property of entanglement has practical applications in the emerging field of quantum computing. Unlike classical computers, which process information in binary bits, either 0 or 1, quantum computers use quantum bits, or qubits, which can exist in multiple states at once thanks to superposition. This allows quantum computers to perform certain calculations much faster than traditional computers. Quantum computing is still in its early stages, but it has the potential to revolutionize fields such as cryptography, drug discovery, and artificial intelligence by solving complex problems that are currently beyond the reach of classical computing. The quantum world also introduces us to the concept of vacuum fluctuations, which challenge our understanding of what nothingness really means. According to quantum theory, even in the vacuum of empty space, particles and antiparticles are constantly popping in and out of existence. These virtual particles are fleeting, appearing and annihilating each other in a matter of moments. But their presence can have measurable effects, such as the Casimir effect, where two uncharged plates placed very close together in a vacuum experience a force pulling them toward each other. This phenomenon shows that even the emptiest regions of space are not truly empty, but seething with invisible activity. As we grapple with the bizarre nature of quantum mechanics, we also turn our attention to the search for unification, the quest to develop a single theory that explains both the large-scale structure of the universe, governed by general relativity, and the behavior of particles at the quantum level, governed by quantum mechanics. One of the most promising candidates for this unification is string theory. String theory posits that the fundamental building blocks of the universe are not particles, but tiny, vibrating strings of energy. These strings can vibrate at different frequencies, giving rise to the various particles and forces we observe. String theory also suggests the existence of additional dimensions beyond the familiar 3 dimensions of space and 1 of time. While the theory has yet to be experimentally proven, it offers an elegant framework that could one day reconcile the contradictions between general relativity and quantum mechanics. The deeper we probe into the nature of the universe, the more we realize how interconnected everything is, from the smallest quantum fluctuations to the largest galactic structures. The concept of cosmic inflation, for example, ties directly into quantum mechanics. During the inflationary period, quantum fluctuations in the early universe were stretched across vast distances, eventually forming the seeds for galaxies and cosmic structures. This connection between the quantum and the cosmic shows that the forces shaping the universe on the grandest scales are intimately linked to the tiniest quantum effects. As our understanding of the universe grows, so too does our ability to explore it. Humanity's reach into space continues to expand with increasingly ambitious missions. One of the most exciting recent developments is the advent of private space exploration. Companies like SpaceX, Blue Origin, and others are pushing the boundaries of space travel, with the goal of making space accessible to more people and eventually establishing a human presence on other planets. SpaceX's Starship, for example, is designed to carry large numbers of people and cargo to destinations such as the Moon, Mars, and beyond. The idea of becoming a multiplanetary species is no longer just a dream. Technological advances are bringing us closer to the day when humans might live and work on other worlds. Mars, in particular, is the primary focus of these efforts. While robotic missions have been exploring the Martian surface for decades, the next step is to send humans to the Red Planet. Mars presents numerous challenges, from its thin atmosphere to its extreme temperatures, but it also holds immense potential. The discovery of water ice on Mars suggests that the planet might have once supported life, and it raises the possibility that humans could one day establish self-sustaining colonies there, using local resources to produce food, water, and fuel. Beyond Mars, humanity's future in space might involve exploring the moons of the outer planets, such as Europa, Titan, or Enceladus, which may harbor subsurface oceans and the potential for life. The exploration of these distant worlds will likely require new technologies, such as advanced propulsion systems and life support mechanisms capable of withstanding the harsh environments of deep space. As we push further into the cosmos, our growing knowledge of space raises profound questions about our place in the universe. Are we alone, or is life a common outcome in the vast stretches of space? What will the future of humanity look like as we continue to explore and expand beyond Earth? These questions inspire both scientific inquiry and philosophical reflection, reminding us that the universe is a place of endless wonder, complexity, and beauty. The pursuit of understanding the universe is not just about answering questions. It's about expanding our sense of possibility. Every discovery, every new theory, brings us closer to grasping the full scope of the cosmos and our role within it. Whether we are searching for life on distant planets, studying the fundamental forces of nature, or contemplating the fate of the universe, one thing is certain: space will always remain the ultimate frontier, and the more we explore it, the more mysteries we will uncover. As we continue our exploration into the farthest reaches of space and the deepest mysteries of the cosmos, the questions we face become not only more profound, but also more personal. One of the most compelling topics in the ongoing study of the universe is the possibility of life beyond Earth. The search for extraterrestrial life, once confined to the realms of science fiction, is now a serious scientific endeavor. From scanning distant exoplanets for signs of habitability to investigating the extreme environments of our own solar system, scientists are actively seeking evidence that we are not alone in the universe. One of the most promising places to search for life is not far from home: the icy moons of the outer planets. Europa, one of Jupiter's moons, has long been considered a top candidate for extraterrestrial life due to its subsurface ocean. Beneath its thick shell of ice, Europa is believed to harbor a vast ocean of liquid water, kept warm by tidal forces exerted by Jupiter's immense gravity. This ocean, rich in the chemical ingredients necessary for life, could potentially support microbial life or even more complex organisms. NASA's upcoming Europa Clipper mission is set to launch in the near future, aiming to study Europa's surface and subsurface in greater detail, using a suite of scientific instruments to determine the moon's habitability. Enceladus, a small moon of Saturn, presents another intriguing possibility. In 2005, the Cassini spacecraft discovered plumes of water vapor, organic molecules, and other materials erupting from the moon's south pole. These geysers are thought to originate from a subsurface ocean beneath Enceladus' icy crust. The presence of water, along with organic compounds, makes Enceladus one of the most exciting targets in the search for life in our solar system. Future missions could potentially sample these plumes directly, giving us the chance to analyze material from Enceladus' ocean without having to drill through its ice. Titan, another of Saturn's moons, is yet another world that challenges our understanding of what conditions are necessary for life. With its thick, nitrogen-rich atmosphere and liquid methane and ethane lakes, Titan is unlike any other body in the solar system. While Titan's surface is far too cold for liquid water, some scientists speculate that life could potentially arise in the moon's hydrocarbon lakes, or that a subsurface ocean of water and ammonia could harbor life. The European Space Agency's upcoming Dragonfly mission will send a rotorcraft to explore Titan's surface, offering an unprecedented look at this alien world. While the moons of Jupiter and Saturn provide exciting prospects for finding life within our own solar system, the search for life beyond the solar system has been supercharged by the discovery of thousands of exoplanets. These are planets that orbit stars other than the Sun, and their discovery has transformed our understanding of planetary systems. Thanks to missions like the Kepler Space Telescope, we now know that planets are incredibly common throughout the galaxy. Many of these exoplanets lie in the so-called habitable zone of their stars, the region where conditions might be right for liquid water to exist, making them prime candidates for the search for life. Among the most promising of these exoplanets is Proxima b, an Earth-sized planet orbiting within the habitable zone of Proxima Centauri. The closest star to the Sun, Proxima b, is located just over 4 light-years away, making it one of the nearest potentially habitable planets we've discovered. While we currently lack the technology to send spacecraft to such distant worlds, ongoing observations of Proxima b are aimed at determining whether it has an atmosphere, and, if so, what kind of conditions exist on its surface. The discovery of Proxima b has fueled speculation that life could exist not just on distant exoplanets, but on planets within the relatively close neighborhood of our own solar system. The discovery of exoplanets has also raised the exciting possibility of detecting biosignatures, chemical signs of life, on distant worlds. In recent years, astronomers have developed techniques to study the atmospheres of exoplanets by observing the way starlight filters through them. Certain chemical compounds, such as oxygen, methane, or water vapor, could indicate the presence of life. The upcoming James Webb Space Telescope, which launched in late 2021, is equipped with the ability to study the atmospheres of exoplanets in unprecedented detail. Scientists are hopeful that, within the next few decades, we might finally detect compelling evidence of life beyond Earth. But while we search for life on other worlds, there is another profound question that drives our curiosity. If intelligent life exists elsewhere in the universe, why haven't we found it yet? This question, known as the Fermi paradox, remains one of the most puzzling in the search for extraterrestrial intelligence. Given the vast number of stars and planets in the galaxy, many of which are older than our own solar system, it seems reasonable to assume that intelligent civilizations should have arisen elsewhere. And yet, despite decades of searching, we have found no clear evidence of other civilizations. There are many possible explanations for the Fermi paradox. One is that intelligent civilizations might be extremely rare, perhaps due to the difficulty of evolving complex life, or the tendency for civilizations to self-destruct before they can reach out to the stars. Another possibility is that intelligent civilizations are deliberately avoiding us, either because they have no interest in contacting less advanced species, or because they are following some form of cosmic quarantine to prevent interference with developing civilizations like ours. Still, others suggest that we may simply be looking in the wrong way. Perhaps advanced civilizations communicate using methods that we have not yet discovered or cannot detect with our current technology. One of the most ambitious efforts to search for extraterrestrial intelligence is the Breakthrough Listen project, which uses some of the world's largest radio telescopes to scan the skies for signals from other civilizations. While no definitive signals have been found so far, the search continues, and each year brings new technological advancements that enhance our ability to detect faint signals from distant stars. The concept of advanced extraterrestrial civilizations also ties into one of the most far-reaching ideas in modern astrophysics, the Kardashev scale. This scale, proposed by Russian astrophysicist Nikolai Kardashev in 1964, categorizes civilizations based on their energy consumption. A Type 1 civilization can harness all the energy available on its home planet. A Type 2 civilization can harness all the energy from its star, and a Type 3 civilization can harness energy on the scale of its entire galaxy. Humanity, by Kardashev standards, is not yet a Type 1 civilization. We still rely on a fraction of the Earth's energy resources, but as our technological capabilities grow, the idea of reaching Type 1 status becomes more plausible. A Type 2 civilization would be able to build structures such as Dyson spheres, hypothetical megastructures that could completely encircle a star, capturing nearly all of its energy output. While Dyson spheres are purely speculative at this point, some astronomers have suggested that the search for such structures could be a way to detect advanced civilizations. If a star's light were to dim in a way consistent with the presence of a Dyson sphere, it could be an indication of a highly advanced society. Moving up the scale, a Type 3 civilization would be so advanced that it could control energy on the scale of an entire galaxy, perhaps even using black holes or manipulating spacetime itself. While this level of technological prowess is far beyond anything we can imagine, it raises profound questions about the future of intelligent life in the universe. Could humanity one day reach such levels of advancement? And if so, what would our place be in the broader galactic community? As we ponder these possibilities, it's important to remember that our search for life and intelligence in the universe is still in its infancy. We have barely scratched the surface of what is possible, and the next few decades promise to be a time of extraordinary discovery. Whether we find microbial life on a moon of Jupiter, detect biosignatures on a distant exoplanet, or receive a signal from an advanced civilization, the impact of such discoveries would be profound. They would forever change our understanding of our place in the cosmos and challenge us to reconsider the nature of life, intelligence, and civilization. The search for life beyond Earth is not just a scientific quest, it's a deeply human one. It speaks to our innate curiosity and our desire to connect with something larger than ourselves. The questions we ask about life in the universe are ultimately questions about ourselves. Where did we come from? Are we alone? What is our future? These questions have driven explorers, philosophers, and scientists for centuries, and they will continue to drive humanity forward as we push further into the final frontier. The universe, with its billions of galaxies and countless stars, is teeming with possibilities. Whether or not we ever find life beyond Earth, the journey of exploration itself will bring us closer to understanding the profound mysteries of existence. Every step we take into the unknown is a reminder of the infinite potential of human discovery and the enduring wonder of the cosmos. As we continue our journey through the mysteries of the cosmos, we encounter increasingly complex and captivating ideas that challenge our understanding of reality itself. One of the most intriguing concepts in modern physics is the idea of multiverses. The multiverse theory suggests that our universe might not be the only one, but rather, it is part of a much larger collection of universes, each with its own set of physical laws and constants. This mind-bending idea comes from various interpretations of quantum mechanics, string theory, and cosmology, and it has profound implications for how we understand the nature of existence. The concept of the multiverse has its roots in the idea of cosmic inflation, the rapid expansion of the universe in the moments after the Big Bang. According to some versions of inflationary theory, different regions of space could have undergone inflation at different rates, creating bubble universes that are separate from one another. These bubble universes would be completely isolated from each other, with no way of traveling between them or even detecting their existence directly. Each bubble could have different laws of physics, different types of matter, and entirely different histories. In one universe, gravity might be stronger, stars might never form, or the fundamental forces of nature might behave in ways that are completely foreign to us. This notion is often referred to as eternal inflation, suggesting that new universes are continuously being created in an ever-growing multiverse. Another version of the multiverse comes from the many-worlds interpretation of quantum mechanics. In this interpretation, every time a quantum event occurs with multiple possible outcomes, the universe splits into a series of parallel universes, with each one representing a different outcome. For example, if you flip a coin, in one universe it lands heads, and in another it lands tails. While these parallel universes exist independently, they are thought to be interconnected at a fundamental level, meaning that all possible versions of reality are playing out somewhere in the multiverse. This interpretation has gained popularity because it provides a solution to the problem of quantum superposition, where particles can exist in multiple states simultaneously until they are observed. String theory, another frontier of theoretical physics, also provides a framework for the existence of a multiverse. In string theory, the fundamental building blocks of the universe are not point-like particles but tiny, vibrating strings of energy. These strings can vibrate in different ways, giving rise to different particles and forces. One of the more striking implications of string theory is that it requires additional dimensions of space, up to 10 or 11, depending on the version of the theory. These extra dimensions might be compactified, meaning they are curled up and too small for us to detect directly. However, different configurations of these dimensions could lead to entirely different kinds of universes, each with its own unique physical properties. While the multiverse remains a speculative idea, it has captivated the imaginations of both scientists and the public. If the multiverse exists, it raises profound questions about the nature of reality, free will, and our place in the cosmos. Are there other versions of ourselves living out different lives in parallel universes? Is every possible decision we make creating a new branch of reality? These questions are not just abstract. They challenge our understanding of causality and the meaning of existence. As we contemplate the multiverse, we must also reckon with the mysteries of dark matter and dark energy, which together make up about 95% of the universe's total energy and mass. Dark matter, which we cannot see directly, exerts a gravitational pull that affects the motion of galaxies and galaxy clusters. Without dark matter, the outer regions of galaxies would fly apart due to their rapid rotation speeds. While we cannot observe dark matter itself, we can detect its gravitational influence on visible matter. The leading candidates for dark matter include hypothetical particles like WIMPs, weakly interacting massive particles, or axions, but so far, no direct evidence of these particles has been found. Dark energy, which is even more mysterious than dark matter, is responsible for the accelerating expansion of the universe. Discovered in the late 1990s, dark energy acts as a kind of anti-gravity, pushing galaxies apart at an ever-increasing rate. One of the most puzzling aspects of dark energy is that it appears to be constant throughout space, suggesting that it might be an intrinsic property of the vacuum itself. Some theories propose that dark energy could be related to the cosmological constant, a term introduced by Einstein in his equations of general relativity. However, the true nature of dark energy remains one of the greatest unsolved problems in modern physics. As we explore these cosmic mysteries, we are also learning more about the fate of the universe. The ultimate fate of the cosmos depends on the amount of dark energy and how it behaves over time. If dark energy continues to drive the expansion of the universe, it could lead to a future where galaxies, stars, and even atoms are torn apart in a scenario known as the Big Rip. Alternatively, the universe could reach a state of eternal expansion, where all stars eventually burn out, and the universe becomes a cold, dark, and empty place, a scenario known as the heat death or Big Freeze. Another possibility is that the expansion could eventually slow down and reverse, leading to a big crunch, where the universe collapses back in on itself, possibly giving rise to another Big Bang in a cyclical process of cosmic birth and death. While the ultimate fate of the universe is still uncertain, our understanding of cosmic evolution has advanced dramatically in recent years. One of the most important discoveries in cosmology has been the detection of the cosmic microwave background, CMB, the faint afterglow of the Big Bang. The CMB provides a snapshot of the universe when it was just 380,000 years old, and its study has given us invaluable insights into the conditions of the early universe. Tiny fluctuations in the CMB reflect the seeds of cosmic structures that would later grow into galaxies, stars, and planets. By analyzing these fluctuations, scientists have been able to estimate the age, composition, and geometry of the universe with remarkable precision. The study of the CMB has also led to a deeper understanding of how galaxies and galaxy clusters formed. In the early universe, matter was almost uniformly distributed, but over time, small density fluctuations grew under the influence of gravity. Dark matter played a crucial role in this process, as it clumped together to form the scaffolding upon which visible matter would later accumulate. The result is the large-scale structure of the universe we see today, with galaxies distributed along vast filaments and sheets, separated by enormous voids. At the center of many galaxies, including our own Milky Way, lies a supermassive black hole. These behemoths, with masses millions or even billions of times that of the Sun, are thought to have formed early in the history of the universe. Supermassive black holes exert a powerful influence on their surroundings, shaping the evolution of their host galaxies. In some cases, material falling into the black hole can form an accretion disk, which heats up and emits tremendous amounts of energy, producing what we call quasars. Quasars are some of the brightest objects in the universe and are typically found in distant galaxies, giving us a glimpse of the early stages of galaxy formation. As we peer deeper into space, we also look back in time, since the light from distant objects takes billions of years to reach us. This means that when we observe galaxies billions of light years away, we are seeing them as they were billions of years ago. This look-back time allows astronomers to study the evolution of galaxies and trace the history of the universe. One of the most exciting recent discoveries has been the detection of gravitational waves, ripples in space-time caused by the acceleration of massive objects like merging black holes or neutron stars. These waves, first predicted by Einstein, were directly detected by the LIGO experiment in 2015, opening a new window on the universe. Gravitational waves allow us to study cosmic events that are invisible to traditional telescopes, such as the collisions of black holes, providing new insights into the most extreme environments in the cosmos. As we continue to explore the universe, it becomes clear that each new discovery brings with it a host of new questions. The more we learn, the more we realize how much is left to discover. Whether we are investigating the smallest particles or the largest cosmic structures, the mysteries of space challenge us to rethink our understanding of reality. From the possibility of multiple universes to the nature of dark matter and dark energy, the universe is a place of infinite complexity and wonder. In the coming decades, new technologies will allow us to probe the cosmos in even greater detail. The James Webb Space Telescope, for instance, is designed to study the earliest galaxies, the formation of stars and planets, and the atmospheres of distant exoplanets. As we explore these frontiers, we may finally answer some of the most profound questions about the origins of the universe and the possibility of life elsewhere. But for every question we answer, new mysteries will undoubtedly emerge, ensuring that the exploration of space will remain one of humanity's greatest endeavors for generations to come. The universe, with its vastness and complexity, continues to inspire awe and curiosity. Whether we are searching for life on distant worlds, contemplating the multiverse, or studying the fundamental forces that shape reality, our quest for knowledge is boundless. Space, in all its mystery and majesty, offers an endless horizon of discovery, reminding us that the more we explore, the more we come to understand the profound and intricate beauty of the cosmos. As we continue to explore the farthest reaches of space and delve deeper into the mysteries of the cosmos, we encounter ideas that push the boundaries of human understanding. One of the most thought-provoking concepts is time itself, and how our perception of it is challenged by the vast scales of the universe and the strange effects of relativity. Time is not a constant, fixed entity as we often experience in our everyday lives. Instead, it can stretch, shrink, or even stand still depending on where you are in the universe and how fast you're moving. According to Einstein's theory of general relativity, time is intertwined with space in a four-dimensional fabric known as space-time. Massive objects like planets, stars, and black holes warp this fabric, bending the flow of time itself. This effect, known as gravitational time dilation, means that time moves more slowly in stronger gravitational fields. For example, if you were to spend time near a black hole, time would pass much more slowly for you compared to someone far away. This phenomenon, while theoretical for black holes, has been proven on a smaller scale here on Earth. Experiments with highly accurate atomic clocks placed at different altitudes have shown that clocks run slightly faster at higher altitudes, where Earth's gravitational pull is weaker. Perhaps the most extreme example of how time can behave differently in space involves black holes, particularly the regions near their event horizons, the point beyond which nothing, not even light, can escape. As you approach the event horizon, from your perspective, time would seem to pass normally. However, to a distant observer, you would appear to slow down more and more as you neared the event horizon, eventually seeming to freeze in time. This strange warping of time is one of the most dramatic examples of how differently the universe behaves when subjected to intense gravitational forces. Black holes, which are already among the most fascinating objects in the universe, continue to surprise us with their bizarre properties. One of the greatest mysteries involving black holes is what happens to information that falls into them. In classical physics, information about the physical state of an object, its energy, position, momentum, cannot be destroyed. However, when an object crosses a black hole's event horizon, it seems as though all information about it is lost. This apparent violation of the principle of information conservation has led to the famous black hole information paradox. Recent theoretical work has suggested that the information might not be lost after all. Instead, it could be encoded in subtle fluctuations on the event horizon itself, or perhaps in holographic patterns that store the information on the surface of the black hole. This idea ties into the holographic principle, a concept that proposes that the entire universe could be described as a two-dimensional structure that encodes all the information of our three-dimensional reality, like a hologram. While this remains speculative, it offers a tantalizing glimpse into the deep connections between quantum mechanics and the nature of space-time. Another mind-bending concept tied to black holes is the idea of white holes. While black holes are regions of space where nothing can escape, white holes are theoretical objects where nothing can enter. A white hole would be the reverse of a black hole, expelling matter and energy rather than consuming it. Although no white holes have been observed, they emerge as possible solutions to the equations of general relativity. Some theories even suggest that black holes and white holes could be connected by a wormhole, providing a passage from one region of space-time to another. This connection, if it exists, would be an example of a bridge through space-time, linking different points in the universe in ways that seem impossible according to our current understanding of physics. While white holes and wormholes remain speculative, the exploration of time and space takes us back to a profound question: is time itself an illusion? Some physicists argue that the passage of time is a human construct, a way for our brains to make sense of the world. According to this view, past, present, and future all exist simultaneously in what is known as the block universe theory. In this model, time is like a landscape, with all events, past, present, and future, existing at once. We perceive time as flowing because of our limited perspective, much like how we perceive space as three-dimensional, even though it may have more dimensions hidden from us. While the nature of time is still debated among physicists, time travel remains a popular topic in both science fiction and scientific speculation. General relativity allows for the possibility of time travel under certain conditions. For instance, traveling at speeds close to the speed of light would slow down time for the traveler relative to someone who remains stationary, effectively allowing them to travel into the future. This effect, known as time dilation, has been confirmed in experiments with high-speed particles and astronauts in orbit around Earth, who experience time slightly more slowly than people on the surface. Traveling into the past, however, presents more challenges. Many solutions to the equations of general relativity permit closed time-like curves, theoretical paths through space-time that could allow an object to loop back to an earlier point in time. However, these solutions often involve exotic conditions, such as the presence of negative energy or infinitely long, rotating cosmic strings. The potential for paradoxes, such as the famous grandfather paradox, where a time traveler could theoretically prevent their own existence by altering the past, complicates the idea of backward time travel even further. While no evidence for time travel exists, the mathematical possibility keeps the idea alive in theoretical physics. While contemplating time's mysteries, we cannot overlook the equally perplexing enigma of dark matter. As we've mentioned before, dark matter makes up about 85% of the matter in the universe, yet we cannot see or directly detect it. We know it exists because of its gravitational effects on visible matter, such as the way it holds galaxies together. But what is dark matter? Scientists have proposed several candidates for dark matter, including WIMPs, axions, and sterile neutrinos, but so far, none of these particles have been detected. Some theories even suggest that dark matter could be made up of primordial black holes, tiny black holes that formed in the early universe. The search for dark matter has led scientists to conduct experiments deep underground or in space, where the background noise from cosmic rays and other sources can be minimized. These experiments aim to catch glimpses of dark matter particles interacting with ordinary matter. While these searches have yet to yield definitive results, each experiment brings us closer to solving one of the greatest mysteries of modern astrophysics. As mysterious as dark matter is, dark energy presents an even greater puzzle. While dark matter pulls galaxies together, dark energy drives them apart, accelerating the expansion of the universe. What is dark energy? Could it be a new form of energy that permeates all of space? Or could it be a manifestation of something even stranger, such as a modification of gravity itself on the largest scales? Solving the mystery of dark energy could revolutionize our understanding of the universe and answer fundamental questions about the fate of the cosmos. As we look forward to the future of space exploration, the idea of human settlement on other planets moves closer to reality. Mars, the red planet, remains the most likely candidate for humanity's first colony outside Earth. The discovery of water ice on Mars, along with advances in technology, has spurred plans for future missions aimed at not just exploring the planet, but establishing a permanent human presence there. NASA, SpaceX, and other organizations are developing plans for crewed missions to Mars, which could happen within the next few decades. The challenges are enormous, ranging from radiation exposure to the need for sustainable life support systems. But the dream of becoming a multiplanetary species is slowly turning into a practical goal. Establishing a human presence on Mars could be the first step toward the long-term survival of our species. Earth, despite being our cradle, is vulnerable to natural disasters, climate change, and other threats. Colonizing other planets could provide a backup plan for humanity, ensuring that our civilization continues even if catastrophe strikes on Earth. Beyond Mars, other moons and planets in our solar system might one day host human settlements. Titan, Saturn's largest moon, with its thick atmosphere and vast lakes of liquid methane, presents a unique challenge, but also an intriguing possibility for exploration. Europa, with its subsurface ocean, might be a key location for searching for life, while asteroids could provide valuable resources for future space industries. The idea of colonizing other worlds touches on another profound question. How will humanity evolve as we move beyond Earth? In the distant future, as we adapt to new environments on other planets, it's possible that humans could diverge into new species, shaped by the gravity, atmosphere, and radiation of different worlds. Genetic engineering, artificial intelligence, and other advanced technologies could accelerate this process, leading to forms of life that are radically different from anything we currently imagine. As we stand on the cusp of this new era of exploration, we are reminded that the mysteries of space are not just about distant galaxies or exotic physics. They are about us. They challenge our understanding of who we are, where we came from, and where we are going. Every discovery, every new mission, brings us closer to answering the age-old questions of existence and opens the door to new possibilities that we have yet to even dream of. The universe, in all its vastness, is both a destination and a mirror, reflecting the infinite potential of human curiosity and imagination. As we continue to explore the final frontier, we are bound to uncover more surprises, more challenges, and more wonders that will inspire us to keep pushing the boundaries of what we know and what we can achieve. As our journey through the cosmos advances, we confront even more intricate and awe-inspiring ideas, ones that not only expand our understanding of the universe, but also invite us to reconsider the very fabric of reality. One such idea is the nature of the fundamental forces that govern everything from the tiniest subatomic particles to the largest cosmic structures. These forces, gravity, electromagnetism, and the strong and weak nuclear forces, work in harmony to create the universe we observe, but their interactions remain one of the biggest puzzles in modern physics. The search for a theory of everything, a framework that unites these forces under a single umbrella, has been one of the holy grails of science. Currently, we have two highly successful theories: general relativity, which describes gravity and the large-scale structure of the universe, and quantum mechanics, which governs the behavior of particles on the smallest scales. However, these two theories are fundamentally incompatible with each other. General relativity explains gravity as the curvature of space-time caused by mass and energy, while quantum mechanics deals with probabilities and uncertainties in a fundamentally different way. The challenge lies in reconciling these two vastly different descriptions of the universe into a single coherent theory. One of the most promising candidates for unification is string theory, which proposes that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings of energy. These strings can vibrate at different frequencies, giving rise to the particles and forces we observe. What makes string theory so compelling is that it naturally incorporates gravity, something that other quantum theories have struggled to do. However, string theory also predicts the existence of extra dimensions, beyond the 3 dimensions of space and one of time that we are familiar with. These extra dimensions are thought to be compactified, meaning they are curled up so tightly that they are too small to detect directly. If string theory is correct, the universe may have as many as 10 or 11 dimensions, a concept that is difficult to visualize but mathematically consistent. While string theory offers an elegant solution to many of the problems in theoretical physics, it remains largely untested. The energy scales at which string theory becomes relevant are far beyond the reach of current experiments, making it difficult to confirm or falsify. Some critics argue that without experimental evidence, string theory remains more of a mathematical construct than a physical theory. Nevertheless, it continues to be a leading area of research, with the hope that future discoveries will provide insights that bring us closer to a true theory of everything. As we explore the universe's fundamental forces, we are also learning more about its mysterious composition. One of the greatest ongoing puzzles in astrophysics is the nature of dark matter and dark energy, which together make up about 95% of the universe's total mass energy content. Ordinary matter, the stuff that makes up stars, planets, and everything we can see, accounts for just 5%. The rest is invisible and detectable only through its gravitational effects. Dark matter, which we've discussed before, is thought to be made of some form of exotic particle that interacts very weakly with ordinary matter. Despite decades of searching, scientists have yet to detect dark matter directly. However, its presence is inferred from the way galaxies rotate and from the gravitational lensing of light as it passes near massive objects. Gravitational lensing, where the gravity of dark matter bends the path of light from distant galaxies, provides some of the most compelling evidence for its existence. Dark energy, on the other hand, is even more mysterious. Discovered in the 1990s, dark energy is responsible for the accelerated expansion of the universe. This expansion is counterintuitive, as gravity should be pulling everything together. Instead, dark energy seems to be pushing galaxies apart at an ever-increasing rate. What is dark energy? Could it be a property of the vacuum of space itself? Or is it some form of energy field that permeates the cosmos? Despite its profound influence on the evolution of the universe, scientists know very little about what dark energy actually is. Understanding dark energy is not just an academic exercise. It has profound implications for the fate of the universe. If the expansion continues to accelerate, the universe could end in what's called the Big Rip. In this scenario, dark energy would eventually become so dominant that it would tear apart galaxies, stars, planets, and even atoms themselves. Alternatively, dark energy might weaken over time, leading to a big freeze, where the universe continues to expand but at a slower rate, eventually becoming cold, dark, and empty as all the stars burn out. Another possibility is that the expansion might reverse, leading to a big crunch, where the universe collapses back in on itself, potentially starting the cycle over again with a new Big Bang. As we contemplate the fate of the universe, we also turn our attention to one of the most tantalizing questions in science. Are we alone in the universe? The search for extraterrestrial life has evolved from speculation to a serious scientific endeavor. We now know that planets are common throughout the galaxy, thanks to missions like Kepler and TESS, which have discovered thousands of exoplanets orbiting distant stars. Many of these planets lie in the habitable zone, where conditions might be right for liquid water to exist, raising the possibility of life. One of the most exciting developments in this search is the study of exoplanet atmospheres. By analyzing the light that passes through a planet's atmosphere as it transits in front of its star, scientists can detect the presence of certain gases, such as oxygen, methane, and water vapor, potential biosignatures that could indicate life. The James Webb Space Telescope, which launched in 2021, is designed to study these distant atmospheres in unprecedented detail. As we gain the ability to detect more subtle chemical signatures, we may one day find compelling evidence of life on a distant world. While the discovery of microbial life would be groundbreaking, the search for intelligent extraterrestrial civilizations is perhaps even more intriguing. For decades, scientists have been listening for signals from other civilizations through programs like SETI, Search for Extraterrestrial Intelligence. So far, no definitive signals have been detected, leading to the famous Fermi paradox. If intelligent life is common in the universe, why haven't we found it yet? There are many potential answers to this paradox. One possibility is that intelligent civilizations are extremely rare, either because life itself is rare or because the evolution of intelligent life is an exceedingly unlikely event. Another possibility is that civilizations tend to self-destruct shortly after developing advanced technology, whether through war, environmental collapse, or some other catastrophe. Alternatively, it could be that other civilizations are simply not interested in communicating with us, or that they are using communication methods that we are not yet capable of detecting. One of the most thought-provoking ideas is that advanced civilizations might exist in ways that are completely beyond our comprehension. They may have evolved to a point where they no longer need physical bodies or technology as we understand it. They could exist as pure energy, or even as digital consciousnesses, living in vast, self-sustaining virtual worlds. If this is the case, they might not be detectable by any means we currently have at our disposal. This brings us to the concept of the Kardashev scale, which categorizes civilizations based on their energy consumption. A Type 1 civilization can harness all the energy available on its home planet. A Type 2 civilization can harness the energy of its star, and a Type 3 civilization can control energy on the scale of its entire galaxy. Humanity, by this measure, is not even a Type 1 civilization yet, as we have not yet learned to fully exploit the energy resources of Earth. The idea of a Type 2 or 3 civilization raises the possibility that there are beings out there who are so advanced that their actions and technology might appear godlike to us, or they might be entirely uninterested in communication. Another perspective suggests that intelligent civilizations might be intentionally avoiding contact with us, a theory known as the zoo hypothesis. According to this idea, more advanced civilizations may be aware of our existence, but have chosen to leave us alone, perhaps to allow our society to evolve naturally without interference. This could be a form of cosmic prime directive, similar to the one imagined in science fiction, where less advanced civilizations are observed but not interfered with. As we continue to ponder these possibilities, we are reminded that the search for extraterrestrial life, whether microbial or intelligent, is not just about answering scientific questions, but about understanding our place in the cosmos. Are we a unique accident, or part of a vast network of life scattered throughout the universe? The discovery of even the simplest form of life beyond Earth would have profound implications for our understanding of biology, evolution, and the potential for life in environments radically different from our own. The more we explore the universe, the more we realize how much remains unknown. Space, with its vastness and complexity, continues to challenge our understanding at every level, from the quantum to the cosmic. The search for dark matter, the mysteries of dark energy, the potential for extraterrestrial life, and the quest for a unified theory of physics all remind us that the universe is far stranger, more beautiful, and more intricate than we could have ever imagined. As we push the boundaries of exploration, we are entering a new era of discovery. The questions we ask today may lead to answers that redefine our understanding of the universe and our place within it. And with every new discovery, we will continue to unlock the secrets of the cosmos, uncovering new mysteries that challenge us to explore further and dream bigger. The universe is not only the ultimate frontier, but also the ultimate mystery, one that will inspire humanity to continue reaching for the stars for generations to come. As our exploration of the universe continues, we are drawn ever deeper into the mysteries of existence, with each new discovery raising more questions about the nature of reality, time, and space. One of the most tantalizing aspects of this journey is the increasing possibility that we may one day answer one of humanity's oldest and most profound questions. What is the origin of everything? This question encompasses not only the origins of life and the formation of stars and galaxies, but also the deeper, more elusive question of how the universe itself came into being. At present, the dominant scientific explanation for the origin of the universe is the Big Bang Theory, which posits that the universe began as an infinitely small, hot, and dense point around 13.8 billion years ago. From this singularity, the universe rapidly expanded, cooled, and began to form the fundamental particles and forces that eventually led to the formation of atoms, stars, galaxies, and, ultimately, life. The discovery of the cosmic microwave background, CMB, radiation in 1965, a faint glow that permeates the universe and represents the afterglow of the Big Bang, provided strong evidence for this theory. The CMB offers a window into the early universe, allowing scientists to study the conditions that existed only 380,000 years after the Big Bang. However, while the Big Bang Theory explains much about the evolution of the universe from its earliest moments, it leaves many questions unanswered. For instance, what caused the Big Bang? What existed before it? And is the Big Bang a unique event? Or could there be other universes beyond our own, each with its own Big Bang? To address these questions, scientists have developed a number of theories that seek to extend our understanding of the universe's origins. One of the leading ideas is the concept of cosmic inflation, which proposes that a fraction of a second after the Big Bang, the universe underwent a period of extremely rapid expansion. During this brief moment of inflation, the universe grew exponentially, smoothing out any irregularities and setting the stage for the formation of galaxies and large-scale structures. This theory helps explain why the universe appears so uniform on large scales, despite the chaotic conditions that likely existed in its earliest moments. But cosmic inflation also opens the door to an even more mind-bending possibility: the idea of a multiverse. According to some interpretations of inflationary theory, the rapid expansion of space may have occurred differently in different regions, leading to the creation of multiple, separate universes, each with its own unique physical properties. This eternal inflation suggests that our universe is just one bubble in a much larger multiverse, where different regions of space might follow entirely different laws of physics. In some universes, gravity could be stronger or weaker, stars might never form, or the fundamental constants of nature might be completely different, creating realities that are unimaginable from our perspective. The multiverse hypothesis, while speculative, is supported by some versions of string theory, which also predicts the existence of multiple universes. In string theory, the extra dimensions that are required by the theory could give rise to different vacua, regions of space with different configurations of these dimensions, leading to different universes with different physical laws. While we currently have no way of observing these other universes directly, the idea of a multiverse has profound implications for our understanding of reality, raising questions about whether our universe is just one of many, or whether we are living in a unique cosmic bubble. The concept of a multiverse also ties into the anthropic principle, which attempts to explain why the physical constants of our universe appear to be so finely tuned for life. For instance, if the strength of gravity or the electromagnetic force were slightly different, stars might not form, and life as we know would be impossible. The anthropic principle suggests that we observe these finely tuned conditions because, in a multiverse with countless different universes, we happen to live in one where the conditions are right for life. In other words, our universe might not be special or designed for life. It just happens to be one of the rare universes where life can exist. While these ideas stretch the boundaries of current science, they also challenge us to rethink our place in the cosmos. If the multiverse exists, then our universe is not the only possible reality, and we are part of a much larger, more complex structure that we are only beginning to glimpse. This possibility raises philosophical and existential questions as well. If there are infinite universes, each with different outcomes, what does that mean for the concept of free will, identity, and the meaning of life? As we explore these cosmic questions, we are also learning more about the smallest building blocks of the universe. One of the most exciting areas of research in modern physics is the study of quantum mechanics, which governs the behavior of particles at the smallest scales. Quantum mechanics has revealed a world that is far stranger and more unpredictable than anything we experience in our everyday lives. Particles can exist in multiple states at once. They can be entangled in such a way that the state of one particle is instantly connected to the state of another, no matter how far apart they are, and they can tunnel through barriers that should be impenetrable according to classical physics. One of the most famous mysteries of quantum mechanics is the so-called wave-particle duality, where particles such as electrons and photons can behave both as particles and as waves, depending on how they are observed. This duality is most famously demonstrated in the double-slit experiment, where particles passing through two slits can create an interference pattern, behavior typically associated with waves. However, when the particles are observed, they behave like individual particles, and the interference pattern disappears. This experiment reveals the deeply counterintuitive nature of quantum mechanics and suggests that the act of observation itself plays a crucial role in determining the outcome of quantum events. Quantum mechanics has also given rise to one of the most bizarre concepts in physics: quantum entanglement. When two particles become entangled, their properties become linked in such a way that measuring the state of one particle instantly determines the state of the other, even if they are light years apart. This spooky action at a distance, as Einstein famously called it, appears to violate the principle that nothing can travel faster than the speed of light. However, experiments have repeatedly confirmed the reality of entanglement, and it has become a foundational concept in the emerging field of quantum information science. One of the most exciting potential applications of quantum mechanics is quantum computing. Unlike classical computers, which use bits that represent either a 0 or a 1, quantum computers use qubits, which can exist in multiple states simultaneously thanks to superposition. This allows quantum computers to perform certain calculations much faster than classical computers, potentially revolutionizing fields such as cryptography, material science, and artificial intelligence. Although quantum computers are still in their infancy, recent breakthroughs suggest that practical quantum computing could become a reality within the next few decades. As we continue to explore both the smallest scales of the quantum world and the largest scales of the cosmos, we are reminded of how interconnected these realms are. The physics that governs the behavior of particles at the quantum level is intimately tied to the structure and evolution of the universe itself. For instance, quantum fluctuations in the early universe are thought to have seeded the formation of galaxies, stars, and planets. These tiny fluctuations, amplified by cosmic inflation, created the large-scale structure of the universe that we observe today. The interplay between the quantum and the cosmic is also seen in the study of black holes, which remain one of the most mysterious objects in the universe. Black holes are formed when massive stars collapse under their own gravity, creating a region of space where the gravitational pull is so strong that nothing, not even light, can escape. The boundary of a black hole is known as the event horizon, and beyond this point, the laws of physics as we understand them break down. One of the most intriguing aspects of black holes is the information paradox, which arises from the fact that, according to quantum mechanics, information cannot be destroyed. However, when something falls into a black hole, it appears that all information about it is lost forever. This paradox has led to intense debate among physicists, with some proposing that the information is somehow preserved on the event horizon in a form of holographic encoding, while others suggest that the information could be released as the black hole slowly evaporates through a process known as Hawking radiation. Hawking radiation, named after physicist Stephen Hawking, is a theoretical process in which black holes emit radiation due to quantum effects near the event horizon. Over time, this radiation causes the black hole to lose mass and eventually evaporate. While Hawking radiation has not yet been observed directly, its existence is supported by strong theoretical arguments and provides a tantalizing glimpse into the deep connections between quantum mechanics and general relativity. As we explore these mysteries, we are constantly reminded that the universe is far more complex and beautiful than we can currently comprehend. Every new discovery, from the behavior of particles to the structure of the cosmos, challenges our understanding and opens new doors to exploration. Whether we are investigating the origins of the universe, the nature of black holes, or the potential for life on other worlds, the quest for knowledge drives us forward, ever deeper into the unknown. The more we learn, the more we realize how much there is left to discover. The universe is not only vast and expansive, but also full of hidden wonders that we are only beginning to uncover. As we continue our journey into space, we will undoubtedly encounter new surprises, new challenges, and new opportunities to expand our understanding of the cosmos and our place within it. The exploration of the universe is not just a scientific endeavor. It is a journey of discovery that touches on the deepest questions of existence, meaning, and the nature of reality itself. As our exploration of the universe deepens, we move toward the most complex and fascinating frontiers of both science and philosophy, touching on questions that span the very nature of existence, the limits of human understanding, and the ultimate fate of reality. We are at a point where the mysteries of space intersect with the mysteries of consciousness, where the microcosmic world of quantum physics reveals paradoxes that challenge our perceptions of reality, and where the vast scales of cosmology invite us to ponder the universe's most profound possibilities. One of the most intriguing questions in modern science is the relationship between consciousness and the universe itself. Consciousness, our subjective experience of reality, is something we take for granted in everyday life, yet it remains one of the greatest unsolved mysteries in science. How does the brain produce consciousness? Are humans the only conscious beings in the universe? And what, if any, connection does consciousness have to the fabric of reality? Some scientists and philosophers have proposed that consciousness might be more than just a byproduct of brain activity. Instead, they suggest that consciousness could be a fundamental property of the universe, much like space, time, and matter. This idea, sometimes referred to as panpsychism, posits that consciousness might exist at all levels of reality, from the smallest subatomic particles to the entire cosmos. While panpsychism is still a highly speculative and controversial theory, it raises profound questions about the nature of mind and matter. Could it be that the universe itself has some form of awareness, or that consciousness plays a more integral role in the workings of the cosmos than we currently understand? This leads to another fascinating concept, known as the observer effect, which originates from quantum mechanics. In the quantum world, particles like electrons and photons behave in ways that seem to depend on whether they are being observed. In experiments such as the double-slit experiment, particles can exist in a superposition of states, meaning they are in multiple places at once, until they are measured or observed. The act of observation appears to collapse the superposition into a single outcome, as if the very act of measuring or observing reality influences how it unfolds. The implications of the observer effect are profound. Some interpretations of quantum mechanics suggest that consciousness itself might play a role in shaping reality. This leads to the consciousness causes collapse interpretation, where the conscious act of observation could be what forces particles to settle into a definite state. While most physicists favor interpretations that do not require consciousness to explain the collapse of quantum superpositions, the observer effect remains one of the most puzzling and philosophically rich areas of quantum theory. This brings us to another mind-bending idea: the possibility that our universe is, in some sense, a simulation. The simulation hypothesis, popularized by thinkers like philosopher Nick Bostrom, suggests that it is possible our reality is a computer-generated simulation created by a far more advanced civilization. The basic argument is that if civilizations can reach a level of technological sophistication where they can run detailed simulations of entire universes, and if they have the computational power to run many such simulations, then it is statistically likely that we are living in one of these simulations rather than the real universe. The idea of the universe being a simulation raises profound questions about the nature of reality and free will. If our world is a simulation, who or what created it? What purpose does it serve? And if we are indeed living in a simulated universe, what happens when the simulation ends? While there is currently no direct evidence to support the simulation hypothesis, it remains an intriguing philosophical and scientific thought experiment, one that forces us to question the very nature of existence. In the context of cosmic exploration, these ideas about consciousness and the nature of reality gain even greater significance. As we search for life on other planets and explore the possibility of intelligent extraterrestrial civilizations, we are also implicitly searching for answers to questions about the uniqueness of human consciousness. If we find life elsewhere in the universe, will it share the same type of consciousness we experience? Or could it be radically different, shaped by the environment and evolutionary history of its home planet? And what would it mean if we discovered that consciousness could emerge in non-biological systems, such as artificial intelligence? The question of artificial intelligence, AI, brings us to another critical frontier: the potential for machines to achieve consciousness. AI is rapidly advancing, with machines now capable of learning, reasoning, and even creating in ways that resemble human cognition. But can machines ever truly be conscious, or are they merely simulating the appearance of consciousness? This question touches on the so-called hard problem of consciousness, which asks how subjective experience, or qualia, arises from physical processes. If consciousness is a fundamental property of the universe, as some theories suggest, could it eventually emerge in sufficiently complex artificial systems? Or is consciousness something unique to biological organisms, tied inextricably to the organic structures of the brain? The possibility of AI achieving consciousness also raises ethical and philosophical questions about the future of humanity. If we create conscious machines, how should we treat them? Will they have rights and responsibilities? And how will the relationship between humans and machines evolve as AI becomes more sophisticated? The development of conscious AI could profoundly reshape society, culture, and even our understanding of what it means to be human. As we push the boundaries of both artificial and biological life, we must also consider the future of humanity beyond Earth. The colonization of other planets, particularly Mars, is becoming an increasingly realistic goal. While the challenges of establishing a permanent human presence on Mars are immense, from the need to develop sustainable life support systems to protecting colonists from radiation, the idea of humans living and thriving on another world is no longer confined to science fiction. The long-term implications of space colonization are both exciting and daunting. Establishing human colonies on other planets could ensure the survival of our species in the face of potential existential threats, such as asteroid impacts, pandemics, or nuclear war. But it also raises questions about how humanity will evolve in different environments. Will humans who settle on Mars or other distant worlds eventually become distinct species, shaped by the gravity, atmosphere, and conditions of their new homes? And how will we handle the ethical and political challenges that come with expanding human civilization beyond Earth, such as issues of resource allocation, governance, and environmental stewardship? The idea of humans evolving into multiple species over time, shaped by the environments of different planets, is a fascinating one. Just as humans adapted to different environments on Earth, leading to the development of diverse cultures and physical traits, future space colonists might evolve to better suit the environments of Mars, the moons of Jupiter and Saturn, or even space habitats far from any planet. Over thousands or millions of years, these adaptations could result in new forms of human life, raising profound questions about identity, culture, and what it means to be human. As we look even further into the future, we are confronted with the possibility of humanity not only spreading throughout the solar system, but also exploring other star systems. The discovery of exoplanets, planets orbiting stars outside our solar system, has opened up the possibility that one day we may find Earth-like worlds capable of supporting life. Missions like Breakthrough Starshot, which aims to send tiny spacecraft to the nearest star system, Alpha Centauri, within a few decades, represent the first steps toward interstellar exploration. The challenges of interstellar travel are immense, primarily because of the vast distances involved. Even traveling at a fraction of the speed of light, it would take decades or centuries to reach the nearest stars. However, advances in propulsion technology, such as ion drives, nuclear fusion, or even speculative concepts like warp drives, could one day make interstellar travel a reality. If humanity can overcome these challenges, we could one day become a spacefaring civilization, exploring the galaxy and perhaps even encountering other intelligent species along the way. The search for extraterrestrial intelligence, or SETI, continues to be one of the most exciting and enigmatic fields of scientific inquiry. While we have not yet detected any signals from alien civilizations, the discovery of life elsewhere in the universe, whether microbial life on Mars or a signal from a distant star system, would fundamentally alter our understanding of our place in the cosmos. It would answer one of humanity's oldest questions: are we alone in the universe? And if we are not, how do we communicate with and relate to other intelligent species that may be vastly different from us? In addition to the search for extraterrestrial life, the study of exoplanets is revealing a wide variety of planetary systems, many of which are unlike anything found in our solar system. Some exoplanets are hot Jupiters, gas giants that orbit very close to their stars, while others are rocky, Earth-sized planets in the habitable zones of their stars. The diversity of exoplanets suggests that there are many different paths to planetary formation and evolution, some of which may lead to life under conditions we have not yet imagined. As we continue to search for life and explore the farthest reaches of space, we are reminded that the universe is full of possibilities that stretch our imagination and challenge our understanding. The mysteries of consciousness, the potential for life beyond Earth, and the future of humanity as a spacefaring civilization are all part of the larger question of what it means to be a sentient being in a vast, complex, and ever-evolving cosmos. Ultimately, the journey of exploration is not just about answering scientific questions. It is about expanding the boundaries of human experience and understanding. The more we learn about the universe, the more we discover about ourselves. Every new discovery, from the nature of particles to the structure of galaxies, reminds us of the profound interconnectedness of everything in the cosmos and the infinite possibilities that await us as we continue to explore the final frontier. The universe is not only a vast expanse of stars and planets, but a reflection of the deepest mysteries of existence, offering endless opportunities for discovery and wonder as we seek to understand our place in the cosmos. As we continue our journey into the depths of the cosmos and the frontiers of human understanding, we are drawn into a series of profound and far-reaching questions that seem to transcend science alone. We are moving toward a future where humanity may no longer be confined to a single planet, and where the limits of knowledge about the universe, life, and even the nature of reality itself are being continuously challenged and expanded. With each new discovery, we peel back another layer of the universe's mysteries, yet each revelation seems to lead to even more complex questions about our place within the cosmos. One of the most compelling and immediate topics in this era of exploration is the future of humanity in space. The prospect of becoming a multiplanetary species, once the domain of science fiction, is now within our technological and scientific reach. Mars, with its relatively close proximity and its potential to support human life, has become the focal point for space agencies and private companies alike. NASA's Artemis missions, which aim to return humans to the Moon and use it as a stepping stone for future Mars missions, mark a pivotal moment in our history of space exploration. At the same time, companies like SpaceX are pushing the boundaries of space travel, with the goal of not only landing humans on Mars, but eventually creating a sustainable colony. Yet the challenges of colonizing Mars, and, by extension, other planets or moons in our solar system, are enormous. For one, Mars lacks a breathable atmosphere and has only a fraction of Earth's gravity, which could have long-term health effects on the human body. Its surface is bombarded by cosmic radiation due to the lack of a global magnetic field, meaning any long-term habitation would require significant protective infrastructure, such as underground bases or habitats shielded by layers of Martian soil. Moreover, the psychological and social challenges of living in such an isolated and hostile environment could be just as daunting as the technical ones. The human mind has evolved to live in open, dynamic ecosystems, surrounded by other living organisms and a wide range of stimuli. The barren, cold, and desolate landscape of Mars, combined with the sheer distance from Earth, could create significant mental health challenges for those who choose to live there. However, the rewards of colonizing Mars and other celestial bodies far outweigh the risks. The development of space-based industries, such as mining asteroids for rare materials, could revolutionize economies on Earth and provide resources that are scarce here but abundant in space. In addition, establishing a human presence on multiple planets would dramatically reduce the risk of extinction due to natural or man-made catastrophes. As Stephen Hawking famously said, "I don't think we will survive another 1,000 years without escaping beyond our fragile planet." Expanding beyond Earth also challenges us to think about the future evolution of our species. Just as humans have adapted to various environments on Earth, space colonization could lead to new forms of adaptation over time. For instance, humans living on Mars, with its lower gravity and different atmospheric conditions, might evolve to become taller, with lighter skeletal structures and different respiratory systems. Genetic engineering, which is advancing rapidly here on Earth, could play a role in helping humans adapt to space environments more quickly by making us more resistant to radiation, allowing us to process oxygen differently, or even altering our sensory systems to better perceive alien environments. The ethical implications of genetic modification, particularly as it applies to the human species, are profound. Should we alter ourselves in fundamental ways to survive in space? Or should we focus on adapting space to human biology? And if we do genetically modify future generations of space colonists, what does that mean for human identity? Will we see the emergence of distinct, spacefaring subspecies of humans? And how will these groups relate to Earthbound populations? These questions are just beginning to be explored by scientists and ethicists, but they will become increasingly relevant as space colonization moves from theory to reality. While Mars is the most immediate target for human exploration, it is not the only candidate for colonization. The moons of Jupiter and Saturn, such as Europa and Enceladus, hold significant interest for scientists, particularly in the search for extraterrestrial life. These moons are thought to harbor vast subsurface oceans beneath their icy crusts, and the conditions in these oceans could be similar to those that gave rise to life on Earth billions of years ago. Missions to explore these moons, such as NASA's Europa Clipper, are already in development, and future robotic or even crewed missions could one day sample the waters of these distant worlds, searching for signs of life in the darkness beneath the ice. If life exists in the oceans of Europa or Enceladus, it would fundamentally alter our understanding of biology and the conditions necessary for life. It would suggest that life is not limited to Earth-like environments, but can arise in a variety of conditions, expanding the potential for finding life elsewhere in the universe. The discovery of even the simplest microbial life on another world would be one of the most profound discoveries in human history, forcing us to rethink our place in the cosmos and the uniqueness of life on Earth. Beyond our solar system, the search for exoplanets has revolutionized our understanding of planetary systems. We now know that planets are not rare, but rather ubiquitous throughout the galaxy. The discovery of Earth-like planets in the habitable zones of other stars, regions where liquid water could exist, has raised the tantalizing possibility that other civilizations could exist elsewhere in the universe. The Kepler Space Telescope, and more recently, the Transiting Exoplanet Survey satellite tests, have identified thousands of exoplanets, some of which may have the right conditions for life. The next step in the search for life beyond Earth will be the detailed study of exoplanet atmospheres. The James Webb Space Telescope, JWST, with its powerful infrared capabilities, will allow scientists to analyze the atmospheres of distant planets, searching for biosignatures, chemical compounds like oxygen, methane, and carbon dioxide that could indicate the presence of life. Detecting such biosignatures would be an indirect but powerful indication that life exists elsewhere in the universe, even if we are not yet able to directly observe it. While the discovery of microbial life on another planet or moon would be transformative, the search for intelligent extraterrestrial civilizations is perhaps even more intriguing. SETI, the search for extraterrestrial intelligence, has been scanning the skies for decades, looking for signals from other civilizations, but so far, no definitive evidence has been found. The Fermi paradox, the question of why, given the vastness of the universe, we have not yet encountered any signs of intelligent life, remains one of the great unsolved mysteries of science. Various explanations have been proposed, from the idea that intelligent civilizations are exceedingly rare or short-lived, to the possibility that they are deliberately avoiding contact with us. One theory that attempts to explain the Fermi paradox is the Great Filter hypothesis. This suggests that there is some barrier to the development of intelligent life that most civilizations do not overcome. This filter could occur at various stages, From the initial emergence of life to the development of complex intelligence, or even after civilizations have become technologically advanced, if they tend to destroy themselves through war, environmental collapse, or other catastrophes. If the great filter lies behind us, then humanity may be one of the few civilizations to have made it this far. However, if the great filter lies ahead, we may face existential threats that other civilizations failed to survive. The possibility of existential risks is a key reason why many scientists and thinkers advocate for space colonization as a way to ensure the long-term survival of our species. By establishing human settlements on other planets or in space habitats, we could reduce the risks posed by global catastrophes on Earth, such as nuclear war, climate change, or asteroid impacts. In the long run, the survival of humanity may depend on our ability to live beyond our home planet, spreading life to new worlds and ensuring that civilization continues even in the face of adversity. As we contemplate the future of humanity in space, we are also reminded of the deeper, philosophical questions that exploration raises. What will it mean for our sense of identity and purpose when we are no longer confined to a single planet? How will our relationships with each other and with the environment change as we adapt to life in space? Will the vast distances between planets and star systems lead to new forms of isolation, or will they bring us closer together as a species, united in our shared exploration of the cosmos? Space exploration, at its core, is not just about science and technology. It is about pushing the boundaries of human experience and imagination. It forces us to confront the limits of our understanding, to grapple with the vastness of the universe and the fragility of life. As we look up at the stars and plan missions to distant worlds, we are reminded that we are part of something much larger than ourselves, a universe that is ancient, mysterious, and full of possibilities. The journey into space, like the journey of scientific discovery itself, is an endless frontier. Every new question leads to another. Every new discovery opens new doors to exploration. From the smallest quantum particles to the largest galactic structures, the universe is a tapestry of interwoven mysteries that challenge us to think more deeply, to explore further, and to seek answers to the questions that have driven humanity for millennia. As we move forward into the future, we are not just exploring space. We are exploring the very nature of existence itself. Every step we take beyond Earth, every new planet we visit, and every signal we search for in the distant reaches of the galaxy brings us closer to understanding the universe's most profound secrets. And in doing so, we come to understand ourselves better, our place in the cosmos, our potential for growth, and the infinite possibilities that await us as we continue to reach for the stars. As we press further into the cosmic unknown, exploring the mysteries of space and the frontiers of human understanding, we find ourselves standing at the intersection of science, philosophy, and the future of our species. The grand narrative of human exploration is no longer confined to our planet. It has expanded to include not only the physical exploration of other worlds, but also the deep questions about our ultimate destiny as intelligent beings in a universe that remains mostly untamed and unexplored. Each new technological advancement, each new discovery, pushes us closer to understanding some of the most profound questions humanity has ever asked. Where do we come from? Are we alone? And where are we going? At the heart of these questions is the continuing exploration of Mars, which represents both a practical challenge and a profound opportunity for the future of humanity. Mars is the most Earth-like planet in our solar system, with polar ice caps, seasons, and evidence that liquid water once flowed across its surface. However, it is also a planet with extreme environmental challenges. Temperatures far colder than any place on Earth, a thin atmosphere composed mostly of carbon dioxide, and intense radiation from the sun and space. These challenges mean that human colonization of Mars will require unprecedented innovation. But it is precisely this level of challenge that drives human ingenuity. One of the most exciting aspects of Mars exploration is the development of technologies that will allow humans to live and thrive in an environment so different from Earth. From advanced life support systems that generate oxygen and water from the Martian atmosphere, to technologies that harvest energy from the sun or from nuclear power, The challenge of survival on Mars is accelerating the development of technologies that may one day transform how we live on Earth as well. Concepts like in situ resource utilization, which involves using local materials to build habitats or produce fuel, are critical not only for Mars exploration, but for the broader goal of reducing humanity's dependence on Earth's resources. Moreover, the first human missions to Mars will likely involve a level of international cooperation unprecedented in human history. Much like the International Space Station, a Mars mission will require contributions from multiple countries and private organizations, each bringing unique technologies and expertise to the table. This cooperation could pave the way for a new era of global unity, as humanity begins to view itself not just as inhabitants of individual nations, but as citizens of a planet venturing into the wider cosmos. In the coming decades, the arrival of humans on Mars will mark a watershed moment for humanity, much as the Apollo landings did in the 20th century. However, landing on Mars is just the beginning. As we establish a foothold on the red planet, the longer-term goal will be to create a self-sustaining colony, one that can grow its own food, produce its own energy, and develop the infrastructure necessary for long-term habitation. Such a colony will not only represent a technological achievement, but also a philosophical one, as it will raise questions about what it means to live on another world. Will future Martian colonists view themselves as Earthlings, or will they develop a new, distinct identity as Martians? How will their culture, values, and even biology evolve as they adapt to life in an environment so different from Earth? As we consider the potential for Martian colonies, we must also address the ethical implications of human expansion into space. Mars, like the rest of the universe, is pristine and untouched by human hands. Some argue that we have a moral obligation to preserve the natural state of these other worlds, much as we seek to protect Earth's own fragile ecosystems. Others believe that human exploration and settlement are inevitable, and that we should embrace our role as stewards of the universe, balancing exploration with conservation. This debate will only intensify as we move closer to establishing a permanent human presence on Mars, and, eventually, beyond. Looking further into the future, the colonization of Mars could be just the first step in a much larger journey across the solar system. The outer moons of Jupiter and Saturn, such as Europa, Ganymede, and Titan, are among the most intriguing targets for future exploration. Europa, with its subsurface ocean beneath a thick layer of ice, is one of the most promising candidates for finding life in our solar system. Missions to explore these moons, whether through robotic probes or even human missions, could uncover life in forms we have not yet imagined, potentially rewriting our understanding of biology. The discovery of life elsewhere in our solar system, or beyond, would represent a seismic shift in how we understand our place in the universe. Even the detection of microbial life on Mars or Europa would confirm that life is not unique to Earth, and that it can arise in environments vastly different from those we know. But what if we find intelligent life? This question leads us directly into the search for extraterrestrial intelligence, which remains one of the most tantalizing yet elusive goals in modern science. The Fermi paradox, which asks why we have not yet detected signs of intelligent extraterrestrial civilizations despite the vast number of stars and planets in the universe, continues to puzzle scientists. One possible explanation is that intelligent life is extraordinarily rare or short-lived. Civilizations might arise, develop advanced technology, and then destroy themselves before they have the chance to explore the universe or communicate with other species. This idea, known as the Great Filter, suggests that there is some barrier that prevents civilizations from reaching a stage where they can colonize other planets or make contact with distant civilizations. Another possibility is that intelligent extraterrestrial civilizations do exist, but they are deliberately avoiding contact with us. This is known as the zoo hypothesis, which suggests that more advanced civilizations might observe us from a distance, much as we might observe animals in a nature preserve, without interfering in our development. Alternatively, they might use forms of communication that we are not yet capable of detecting, or they might exist in forms that we cannot even recognize. The question of whether we are alone in the universe is not just a scientific one. It is also deeply philosophical. If we are alone, then humanity may be one of the rarest and most precious phenomena in the universe. In that case, the responsibility to preserve and protect life on Earth, and perhaps to spread life to other planets, takes on an even greater significance. If we are not alone, then we must prepare for the possibility of one day encountering other intelligent beings, with their own histories, cultures, and technologies. While the search for extraterrestrial intelligence continues, another question is increasingly occupying the minds of scientists and thinkers. What is the ultimate fate of the universe? The universe, as we know, is expanding, with galaxies moving away from each other at ever-increasing speeds. This expansion is driven by dark energy, a mysterious force that makes up about 70% of the universe's energy density. The discovery of dark energy in the late 1990s was one of the most surprising findings in modern cosmology, and its nature remains one of the greatest unsolved mysteries in physics. If dark energy continues to drive the expansion of the universe, we face a future where galaxies become increasingly isolated from each other, eventually moving beyond the reach of our telescopes. In this scenario, often referred to as the Big Freeze or heat death, the universe will continue to expand until all the stars burn out and all matter eventually decays, leaving behind a cold, dark, and empty cosmos. Alternatively, dark energy could change over time, leading to different scenarios such as a Big Rip, where the expansion accelerates to the point where galaxies, stars, and even atoms are torn apart. On a more speculative level, some theories suggest that the universe could undergo a series of Big Bangs and Big Crunches, with each cycle leading to the birth of a new universe. This idea ties into the concept of the multiverse, where our universe is just one of many, each with its own physical laws and constants. If the multiverse exists, then the death of our universe might simply be one phase in an infinite cycle of creation and destruction. Regardless of the ultimate fate of the universe, our exploration of space is likely to continue for as long as humanity exists. The drive to explore, to push beyond our known boundaries, and to seek out new knowledge is one of the defining characteristics of our species. As we develop new technologies from advanced spacecraft to artificial intelligence, we will become increasingly capable of exploring the farthest reaches of the cosmos, seeking answers to the deepest questions of existence. Artificial intelligence, in particular, may play a crucial role in the future of space exploration. AI systems are already being used to analyze vast amounts of astronomical data, helping scientists identify exoplanets, map galaxies, and understand the behavior of distant stars. In the future, AI could be used to pilot spacecraft, conduct experiments on distant worlds, and even assist in the search for extraterrestrial life. As AI systems become more sophisticated, they may take on roles that go beyond mere assistance, becoming active partners in humanity's exploration of the cosmos. AI also raises another fascinating possibility: the eventual merging of human consciousness with machines. As we develop more advanced brain-computer interfaces and learn more about the nature of consciousness, it is conceivable that future humans might choose to augment their cognitive abilities or even upload their consciousness into digital systems. This raises profound ethical and philosophical questions. What would it mean to be human if our minds could exist outside our biological bodies? Could we one day achieve a form of immortality by transferring our consciousness into machines or even into virtual environments that exist independent of physical space? The exploration of these questions, like the exploration of space itself, is both exciting and humbling. The universe, in all its vastness and complexity, offers endless opportunities for discovery, but it also forces us to confront the limitations of our knowledge and the fragility of our existence. Every new question we ask, every new mystery we uncover, brings us closer to understanding the nature of reality, but it also reveals how much we have yet to learn. As we move forward into the unknown, humanity stands on the brink of a new era, one where the exploration of space, the development of artificial intelligence, and the search for extraterrestrial life will shape the future of our species. This journey is not just about scientific discovery. It is about the pursuit of meaning, the search for our place in the universe, and the ultimate question of what it means to be alive in a cosmos that is as mysterious as it is vast. The future of humanity is intertwined with the future of space exploration. The stars are not just distant points of light. They are destinations, symbols of our innate curiosity, and beacons of the boundless potential that lies within us. As we continue to push the boundaries of what is possible, we may one day find ourselves not only exploring the farthest reaches of the universe, but also discovering the deepest truths about ourselves, our origins, and our destiny among the stars. As we push ever further into the cosmic frontier, our understanding of space, life, and existence itself continues to evolve in ways that both excite and challenge our fundamental assumptions. The universe, vast and ancient, remains a place of boundless mystery and potential. Each new leap in technology, every groundbreaking discovery, takes us closer to unraveling some of the deepest questions humanity has ever faced. What are the ultimate limits of our knowledge? How will we navigate the challenges of becoming an interplanetary species? And what will the future of humanity look like as we move beyond our home world and into the stars? One of the key drivers of this future is the ongoing development of space travel technology. Over the past few decades, private companies such as SpaceX, Blue Origin, and others have transformed the landscape of space exploration, pushing the boundaries of what was once thought possible. Reusable rockets have dramatically lowered the cost of launching payloads into space, while ambitious projects like SpaceX's Starship promise to open the door to human travel to the Moon, Mars, and beyond. The idea of regular, affordable space travel, once confined to the realm of science fiction, is quickly becoming a reality, and this has profound implications for the future of humanity. As we look toward the colonization of Mars, we begin to grapple with the logistics of living on another world. The challenges are immense: creating sustainable habitats, producing food and oxygen, and generating energy in an environment that is hostile to human life. However, each of these challenges also represents an opportunity for innovation. The technologies we develop to live on Mars could revolutionize life on Earth, providing new ways to address some of the most pressing problems we face, such as climate change, resource scarcity, and energy production. One of the most promising areas of research is in situ resource utilization, ISRU, which involves using the materials available on other planets and moons to sustain human life. On Mars, for example, it may be possible to extract water from the soil, generate oxygen from the carbon dioxide-rich atmosphere, and use local minerals to build habitats. By reducing the need to transport large amounts of materials from Earth, ISRU could make space exploration more feasible and sustainable in the long term. It also represents a critical step toward the ultimate goal of creating self-sustaining colonies on other planets, places where humans can live and thrive independently of Earth. Another key challenge is the question of how we will protect humans from the harmful effects of space travel, particularly the dangers posed by cosmic radiation. On Mars, which lacks a global magnetic field and a thick atmosphere, radiation levels are much higher than on Earth, and long-term exposure could have serious health consequences for future colonists. Researchers are exploring a range of solutions, from underground habitats that provide natural shielding, to advanced materials that can block radiation, to genetic modifications that could make humans more resistant to radiation. Each of these approaches brings us closer to creating environments where humans can safely live and work on other planets. Beyond the practical challenges of space colonization, there is also the question of how humans will adapt to life on another planet, both physically and psychologically. Mars, with its lower gravity, thin atmosphere, and extreme temperatures, presents an environment unlike anything humans have ever experienced. Over time, humans living on Mars may begin to develop physical adaptations to these conditions, potentially leading to changes in height, muscle structure, or even metabolism. These changes, while subtle at first, could become more pronounced over generations, raising the possibility that humans who live on Mars for extended periods might eventually become a distinct population, with their own unique characteristics. The psychological challenges of living on Mars could be just as significant as the physical ones. The isolation and confinement of living on a distant planet with limited contact with Earth could take a toll on mental health. Studies of astronauts on the International Space Station have shown that even short-term missions in space can lead to feelings of isolation, depression, and anxiety. On Mars, where communication delays with Earth can stretch to several minutes, and where the landscape is barren and desolate, these challenges could be even greater. Addressing the mental health needs of future colonists will be critical to the success of any long-term mission, and researchers are already exploring ways to create more psychologically supportive environments for people living in space. While Mars is the most immediate target for human exploration, it is by no means the only one. The outer moons of the solar system, such as Europa, Enceladus, and Titan, represent some of the most exciting prospects for future exploration. These moons, with their subsurface oceans and unique chemical compositions, could harbor life in forms very different from what we know on Earth. Missions to these moons, whether robotic or crewed, could reveal new insights into the origins of life and the potential for life elsewhere in the universe. Europa, a moon of Jupiter, is particularly intriguing. Beneath its thick ice shell lies a global ocean of liquid water, kept warm by tidal forces from Jupiter's gravity. This ocean is thought to be in contact with the moon's rocky mantle, creating conditions that could be similar to those found around hydrothermal vents on Earth, places where life thrives despite the absence of sunlight. NASA's Europa Clipper mission, set to launch in the coming years, will study the moon's ice and ocean in unprecedented detail, searching for signs of habitability and possibly even life itself. The discovery of life on Europa, Enceladus, or Titan would have profound implications for our understanding of biology and the uniqueness of life on Earth. It would suggest that life can arise in environments vastly different from our own, and that the universe may be teeming with life in forms we have yet to imagine. Even if we only find microbial life, the confirmation that life exists beyond Earth would forever change our view of the cosmos and our place within it. As we continue our search for life in the solar system, we are also looking beyond to the stars. The discovery of exoplanets, planets orbiting stars outside our solar system, has revealed that planets are not rare but common. There are likely billions of Earth-like planets in the habitable zones of their stars, where conditions could support liquid water and life. The next frontier in exoplanet exploration will involve studying the atmospheres of these distant worlds, searching for biosignatures, gases like oxygen, methane, and carbon dioxide that could indicate the presence of life. The James Webb Space Telescope, JWST, is at the forefront of this search. With its powerful infrared capabilities, JWST will allow scientists to peer into the atmospheres of distant exoplanets, looking for the chemical fingerprints of life. This search is not limited to Earth-like planets. Scientists are also interested in so-called super-Earths, rocky planets larger than Earth but smaller than Neptune, which may have the right conditions for life to evolve. While the discovery of microbial life would be a monumental breakthrough, the search for intelligent life remains one of the most profound and elusive goals in science. SETI, the search for extraterrestrial intelligence, has been scanning the skies for decades, looking for signals from advanced civilizations, but so far, no definitive evidence has been found. The Fermi paradox, which asks why, given the vastness of the universe, we have not yet encountered any signs of extraterrestrial intelligence, remains an open question. One possibility is that intelligent civilizations are simply too far apart in space and time for us to detect. The universe is over 13 billion years old, and the distances between stars are vast, meaning that even if other civilizations exist, they may be too far away for us to communicate with, or they may have existed millions or billions of years before or after our own civilization. Another possibility is that advanced civilizations do not use the types of signals we are searching for, or that they have chosen not to communicate with us for reasons we cannot yet understand. As we continue to search for life and intelligence in the universe, we are also beginning to grapple with the implications of finding it. What would it mean for humanity to discover that we are not alone? How would it change our view of ourselves, our religions, and our philosophies? And how would we respond if we made contact with an extraterrestrial civilization, particularly one that is more advanced than our own? These questions are not just theoretical. They are becoming increasingly relevant as our ability to explore the universe expands. If we do find evidence of life elsewhere in the universe, whether microbial or intelligent, it will force us to rethink our place in the cosmos and our responsibility as stewards of life on Earth. It may also raise ethical questions about how we interact with other life forms, whether on other planets or in our own solar system. In addition to the search for life, we are also beginning to explore new ways of understanding the universe itself. Dark matter and dark energy, which together make up about 95% of the universe, remain some of the greatest mysteries in cosmology. We know that dark matter exists because of its gravitational effects on galaxies and galaxy clusters, but we have yet to detect it directly. Dark energy, which is driving the accelerated expansion of the universe, is even more mysterious. Understanding these phenomena is critical to understanding the future of the universe itself. If dark energy continues to drive the expansion of the universe, we may face a future where galaxies become increasingly isolated from each other, eventually disappearing from view as they move beyond the reach of our telescopes. This big freeze scenario could lead to a universe where all the stars burn out and all matter eventually decays, leaving behind a cold, dark, and empty cosmos. Alternatively, dark energy could change over time, leading to other possible outcomes, such as a big rip, where the expansion becomes so extreme that galaxies, stars, planets, and even atoms are torn apart. As we explore these cosmic mysteries, we are also beginning to ask new questions about the nature of reality itself. Quantum mechanics, with its strange and counterintuitive behavior, has revealed a universe that operates in ways that defy our classical understanding of physics. Particles can exist in multiple states at once. They can be entangled with each other across vast distances, and they can tunnel through barriers that should be impenetrable. One of the most profound questions raised by quantum mechanics is the nature of time and observation. In the quantum world, the act of observation appears to play a key role in determining the outcome of events, a phenomenon known as the observer effect. This raises the possibility that consciousness itself may play a role in shaping reality, a concept that challenges our understanding of the universe and our place within it. As we continue to explore the quantum world, we are also beginning to explore new ideas about the structure of the universe on the largest scales. The multiverse theory, which suggests that our universe may be just one of many, each with its own physical laws and constants, is gaining traction among some physicists. If the multiverse exists, it could explain some of the strange coincidences we observe in the laws of physics, such as why the universe seems so finely tuned for life. The idea of a multiverse raises profound questions about the nature of reality and the limits of human understanding. If there are infinite universes, each with its own version of reality, what does that mean for free will, identity, and the meaning of life? Are we just one version of ourselves, living out one possibility among an infinite number of others? And if so, how do we make sense of our place in this vast, multidimensional cosmos? The future of space exploration, like the future of science itself, is full of unknowns. As we continue to push the boundaries of what is possible, we will undoubtedly encounter new mysteries, new challenges, and new opportunities for discovery. But one thing is certain: the universe, in all its complexity and beauty, will continue to inspire us to explore, to question, and to reach for the stars. This journey, from the surface of Mars to the farthest reaches of the cosmos, is not just about answering scientific questions. It is about expanding the horizons of human experience, about understanding our place in the universe, and about unlocking the potential of life itself. As we venture deeper into space and uncover the secrets of the universe, we are reminded that the ultimate frontier is not just out there in the stars. It is within ourselves, in the infinite possibilities of human curiosity, imagination, and discovery. As we continue to chart our course through the vastness of space and probe the profound depths of existence, we come to realize that the universe is not only a physical landscape, but a conceptual one that challenges every aspect of our understanding, from the nature of reality to the future of intelligence itself. As humanity stands on the cusp of becoming a space-faring civilization, the possibilities that lie ahead are both exhilarating and daunting. The journey ahead will not only redefine our relationship with the cosmos, but may also fundamentally transform what it means to be human. One of the most profound shifts we are likely to face in the coming decades is the growing integration of artificial intelligence, AI, and advanced robotics into the fabric of space exploration. AI has already begun to revolutionize how we explore the universe, From the autonomous rovers that roam the surface of Mars to the algorithms that sift through massive amounts of astronomical data in search of new exoplanets and cosmic phenomena. As AI systems become more sophisticated, they will likely play an even greater role in space exploration, performing tasks that would be too dangerous, complex, or time-consuming for humans. The potential for AI in space extends far beyond data analysis and exploration. In the not-so-distant future, AI could become an indispensable partner in our quest to colonize other worlds. Autonomous systems could help build habitats, manage life support systems, and ensure the smooth functioning of colonies on Mars, the Moon, or other celestial bodies. Robots capable of repairing themselves and adapting to new environments could be essential for long-term survival in the harsh conditions of space, where human intervention may not always be possible or practical. But as AI becomes more deeply embedded in the fabric of space exploration, we are also confronted with the question of whether AI itself could one day evolve to the point of becoming truly conscious. Consciousness, the inner experience of being aware, is something we currently associate with biological organisms, particularly humans. But if AI systems continue to advance, could they eventually achieve a form of machine consciousness? And if so, what ethical obligations would we have toward these conscious machines? The question of whether machines can become conscious raises deep philosophical and ethical concerns. If a machine can think, feel, or have subjective experiences, it might require the same rights and protections we afford to humans. Furthermore, the development of conscious AI could blur the line between human and machine, forcing us to rethink our own identity as a species. Will we one day consider AI to be equal partners in our exploration of the cosmos, or will they remain tools we use to extend our capabilities? One of the most fascinating possibilities is that the future of humanity may not be biological at all. As we continue to push the boundaries of AI and biotechnology, some scientists and futurists have speculated that humans could eventually merge with machines, creating a new form of hybrid intelligence that transcends the limitations of the human brain. Brain-computer interfaces, already in their infancy, could allow us to connect our minds directly to computers, augmenting our intelligence, memory, and creativity in ways that were once the realm of science fiction. This concept, often referred to as transhumanism, envisions a future in which humans transcend their biological limitations through technology. In such a future, we might be able to upload our consciousness into digital systems, effectively achieving a form of immortality by existing as digital beings in a virtual environment. Alternatively, we could enhance our physical bodies with robotic limbs, sensors, or even artificial organs, allowing us to survive in the extreme environments of space without the need for traditional life support systems. Transhumanism brings with it a host of ethical and philosophical questions. If we can augment or even replace our biological bodies with machines, will we still be human? What happens to concepts like identity, consciousness, and free will when our minds can be uploaded into a computer or distributed across multiple systems? And how will society adapt to a world where some individuals choose to enhance themselves while others remain purely biological? The implications of merging with technology go beyond the individual. As we venture deeper into space, it may become necessary for humans to adapt to environments that are radically different from Earth. On planets with lower gravity, different atmospheric compositions, or higher radiation levels, we may need to alter our biology in fundamental ways to survive. Genetic engineering could allow us to modify our DNA to resist radiation or metabolize different elements, while cybernetic enhancements could enable us to communicate directly with machines or control robotic systems with our minds. As we adapt to life in space, humanity itself could evolve into multiple species, each adapted to the unique conditions of the planets and moons they inhabit. The humans of Mars, for example, might develop taller, leaner bodies to cope with the planet's lower gravity, while those living on Europa or Titan might require entirely different adaptations to survive in icy environments or underground oceans. Over time, these adaptations could lead to significant genetic and physiological differences between space-dwelling humans and their Earth-bound counterparts, raising questions about how these divergent populations will interact with one another and with Earth. These changes will not happen overnight, but they represent the long-term trajectory of human evolution as we expand beyond Earth. In the distant future, humanity may become a multi-species civilization, spread across the solar system and beyond, with each population uniquely adapted to its environment. This vision of the future challenges the very concept of what it means to be human, as our descendants may look, think, and live in ways that are almost unrecognizable to us today. Beyond the biological and technological evolution of humanity, there is another possibility that captures the imagination of scientists and futurists alike: the development of a Type 1 civilization. On the Kardashev scale, which measures a civilization's level of technological advancement based on its energy consumption, a Type 1 civilization is one that is capable of harnessing all the energy available on its home planet. Currently, humanity is not yet a Type 1 civilization. We are somewhere around 0.7 on the Kardashev scale, but we are rapidly moving toward that threshold. Becoming a Type 1 civilization would require us to fully utilize renewable energy sources such as solar, wind, and geothermal power, as well as to develop new forms of energy generation that could harness the full power of the Earth's natural systems. This transition would mark a turning point in human history, as we would no longer be constrained by the limitations of fossil fuels or finite resources. Instead, we would have the technological capability to manage and sustain the entire planet's energy needs in a way that is both efficient and sustainable. As a Type 1 civilization, humanity would also have the capability to manage global challenges such as climate change, resource scarcity, and environmental degradation. This level of technological advancement would allow us to stabilize the Earth's ecosystems and ensure the long-term survival of the planet's biodiversity, all while expanding our presence into space. Achieving this level of civilization would require unprecedented cooperation and innovation, as well as a fundamental shift in how we view our relationship with the planet and with each other. Beyond Type 1 lies Type 2, a civilization capable of harnessing the energy of an entire star. This concept, often associated with Dyson spheres or other megastructures, envisions a future where humanity has the capability to capture and utilize the vast amounts of energy radiating from the sun or other stars. Such technology would provide virtually limitless energy, enabling us to build massive space habitats, travel between star systems, and power technologies that are currently beyond our imagination. While we are still far from becoming a Type 2 civilization, the development of solar power, nuclear fusion, and advanced space technologies represents the first steps toward harnessing the power of stars. As we continue to explore the universe, the possibility of becoming a truly star-faring species looms larger on the horizon. If we can learn to harness the energy of entire stars, we may be able to extend our reach to other star systems, exploring exoplanets, mining asteroids, and establishing colonies throughout the galaxy. The idea of becoming a multi-planetary, multi-species, and star-faring civilization brings us back to the fundamental question: what is the ultimate destiny of humanity? As we expand into space and explore the furthest reaches of the cosmos, we are also forced to confront the limitations of our knowledge and the impermanence of our existence. The universe itself, while vast and seemingly eternal, is subject to the same forces of entropy and decay that govern all physical systems. Eventually, even the stars will burn out, galaxies will drift apart, and the universe may face a cold and dark future, a concept known as the heat death of the universe. This raises the question: can humanity survive beyond the lifespan of the universe itself? Some scientists and futurists have speculated that if we achieve a sufficiently advanced level of technology, we might one day be able to transcend the physical universe, either by creating new universes through advanced physics or by transferring our consciousness into digital systems that can survive the death of the universe. These speculative ideas push the boundaries of what we currently understand, but they also represent the ultimate expression of humanity's desire to overcome the limits of space, time, and mortality. In the end, the exploration of space is not just about reaching new destinations. It is about pushing the boundaries of human potential. Every step we take into the cosmos brings us closer to understanding the mysteries of the universe, but it also brings us closer to understanding ourselves. As we look to the stars, we are reminded that our journey is not just about survival. It is about discovery, growth, and the pursuit of meaning in a universe that is both infinite in its possibilities and humbling in its vastness. The future of humanity, whether on Earth, Mars, or in distant star systems, will be shaped by our ability to adapt, innovate, and evolve. The challenges we face, whether they are technological, biological, or philosophical, are part of a larger narrative of exploration and discovery. As we continue to explore the final frontier, we will encounter new worlds, new forms of life, and new ideas that will change the course of human history. But in doing so, we will also continue to explore the most profound frontier of all, the frontier of human potential. In the coming centuries, as we build cities on other planets, explore the farthest reaches of the galaxy, and perhaps even transcend the boundaries of biology and consciousness, we will be writing the next chapter in the story of human civilization. It is a story that began on a small blue planet orbiting a star in the Milky Way, but it is a story that has no end. The universe, with all its mysteries and wonders, is our future, and it is a future filled with infinite possibilities. As long as we continue to look up at the stars, driven by curiosity and the desire to understand, we will always have a destination, a journey, and a purpose among the cosmos. As humanity stands on the threshold of the next great era of exploration, the road ahead, filled with new worlds, advanced technologies, and cosmic mysteries, promises to redefine not only our relationship with the universe but also the very nature of our existence. Each step into space, every scientific breakthrough, and each philosophical contemplation brings us closer to answering age-old questions about life, reality, and the ultimate destiny of intelligent civilizations. As we push beyond the limits of what we thought possible, we begin to see that the future holds infinite potential for discovery, transformation, and evolution. One of the most intriguing aspects of our future in space is the development of large-scale space habitats. While planetary colonization, particularly on Mars, captures much of the public imagination, the construction of massive orbital habitats, artificial worlds designed to house millions, perhaps even billions of people, represents an alternative vision for the future of human settlement beyond Earth. These habitats, often called O'Neill cylinders or Stanford toruses, are vast rotating structures that generate artificial gravity through centrifugal force. They could be built using materials mined from asteroids or the moon and powered by the sun or nuclear fusion. The idea of space habitats offers several advantages over planetary colonization. Unlike planets, which have fixed environments, space habitats can be designed to meet specific human needs. The climate, gravity, and atmosphere of these habitats can be precisely controlled, and they can be positioned in stable orbits near Earth or other planets, making them more accessible. Moreover, space habitats could eventually outnumber planets as population centers, offering a flexible, modular solution to the problem of expanding human civilization throughout the solar system. The construction of space habitats would represent a monumental engineering challenge, but it is not beyond the realm of possibility. With advances in 3D printing, robotics, and materials science, we are approaching the point where the large-scale construction of space infrastructure could become feasible. Asteroid mining, another emerging field, could provide the raw materials needed to build these habitats. By harvesting metals, water, and other resources from asteroids, we could reduce the need to transport materials from Earth, significantly lowering the cost of construction in space. In addition to providing living space for future generations, space habitats could serve as hubs for scientific research, industrial production, and even space tourism. As our knowledge of space travel and resource utilization grows, these habitats could become self-sustaining ecosystems, complete with their own agricultural systems, water cycles, and energy sources. Such self-sufficiency would be essential for long-term space colonization, particularly if humanity plans to expand beyond the inner solar system and establish a presence in the outer planets and beyond. While the construction of space habitats would open up new opportunities for human expansion, it would also raise significant questions about how society, culture, and governance might evolve in such environments. Living in space, detached from the cultural, political, and environmental context of Earth, could lead to the development of entirely new social systems. How will communities in space organize themselves? Will they form new types of governments, economic models, or social norms? The experience of living in a closed, artificial environment could also foster new forms of identity, as space dwellers adapt to the unique challenges and opportunities of life in the cosmos. These questions are not merely speculative. As humanity expands into space, we will need to confront the ethical, political, and social implications of creating new societies and environments that are fundamentally different from Earth. The governance of space colonies, whether on Mars, the Moon, or in orbital habitats, will likely involve a mixture of international cooperation and innovation in political organization. New models of governance, adapted to the realities of space, could emerge, whether they are democratic, meritocratic, technocratic, or something entirely new. At the same time, we must consider the environmental and ethical responsibilities that come with expanding human civilization into space. Space, for now, is a pristine and untouched environment. The planets, moons, and asteroids we explore have never been subjected to the kind of environmental degradation we have caused on Earth. As we move into space, we must learn from our experiences on Earth and ensure that we treat these new worlds with care and respect. The extraction of resources from asteroids and the construction of habitats should be done in a way that minimizes harm to the cosmic environment, even as we expand human activity. As we push deeper into the solar system, the moons of the gas giants, particularly Jupiter's moon Europa and Saturn's moon Titan, offer tantalizing prospects for exploration and colonization. Europa, with its vast subsurface ocean beneath a layer of ice, is one of the most promising locations for finding extraterrestrial life. Missions like NASA's Europa Clipper aim to explore this icy world, searching for signs of habitability and possibly even microbial life. If life is discovered beneath Europa's ice, it would revolutionize our understanding of biology and the conditions under which life can arise. Titan, Saturn's largest moon, presents a different but equally fascinating opportunity. With a thick atmosphere and vast lakes of liquid methane and ethane, Titan is one of the most Earth-like environments in the solar system, albeit far colder and chemically different. Despite its extreme cold, Titan's organic chemistry, based on hydrocarbons, makes it a prime candidate for future exploration. Colonization of Titan could involve living in floating habitats above its methane lakes or building cities within its protective atmosphere, shielded from cosmic radiation. While the colonization of other planets and moons remains a long-term goal, the search for extraterrestrial life, both microbial and intelligent, continues to be one of the most exciting and profound quests in science. The discovery of microbial life elsewhere in the solar system would not only answer one of humanity's oldest questions, but also raise new ones about the nature of life itself. If life can arise on multiple worlds within our own solar system, it suggests that life may be common throughout the galaxy, existing in environments vastly different from Earth's. The search for intelligent extraterrestrial civilizations, however, remains a far more challenging endeavor. The Fermi paradox, which asks why we have not yet encountered any evidence of intelligent life despite the vastness of the universe, continues to puzzle scientists. One explanation is that intelligent civilizations may be rare or short-lived, succumbing to self-destruction before they can explore the stars. Another possibility is that advanced civilizations use forms of communication that we have not yet discovered, or that they choose to remain hidden from us. Some scientists have proposed the idea of post-biological civilizations, advanced species that have transcended their biological origins and uploaded their consciousness into digital or non-physical systems. Such civilizations might be so advanced that they no longer use radio waves or other detectable forms of communication, making them invisible to our current search methods. Alternatively, they may exist in virtual realities of their own creation, uninterested in interacting with the physical universe or other civilizations. This brings us to the concept of virtual worlds and digital realities, which could play a significant role in humanity's future as we explore the stars. As virtual reality, VR, and artificial intelligence continue to advance, it is possible that future humans will spend much of their time in virtual environments, simulations that are indistinguishable from reality. In these virtual worlds, individuals could experience any environment, live out any scenario, and interact with others in ways that transcend the limitations of the physical world. Virtual worlds could also offer a solution to some of the challenges of space exploration. Traveling to distant star systems will likely take centuries, even with the most advanced propulsion technologies. However, digital consciousness or uploaded minds could experience time differently, making long space journeys more bearable. By living in virtual environments while their physical bodies or digital systems travel through space, humans could explore distant star systems without the constraints of biological aging or the psychological challenges of isolation. The idea of virtual worlds also ties into the simulation hypothesis, the theory that our reality might itself be a sophisticated computer simulation. While this idea remains speculative, it raises profound questions about the nature of existence. If we are living in a simulation, what is the purpose of this simulated reality? Who or what created it? And could we ever escape the simulation to discover the true nature of reality? The concept of simulated reality, whether we are living in one or creating our own, challenges our understanding of free will, identity, and the nature of the universe. It suggests that reality itself might be more fluid and malleable than we currently understand, shaped not only by the physical laws of the universe, but also by the intentions and desires of those who create or inhabit these simulations. As we explore these ideas, we must also grapple with the ultimate question: what is the fate of the universe itself? Cosmologists continue to study the long-term evolution of the universe, driven by the mysterious forces of dark matter and dark energy. If dark energy continues to accelerate the expansion of the universe, we may face a future where galaxies drift further and further apart, eventually disappearing from view. Stars will burn out, and the universe will become cold, dark, and empty in a scenario known as the Big Freeze. Alternatively, the universe could undergo a Big Rip, where the expansion becomes so extreme that even atoms and subatomic particles are torn apart. In this scenario, the fabric of space-time itself would be destroyed. A less dramatic, but still existential, possibility is that the universe will reach a state of thermodynamic equilibrium, where all energy is evenly distributed and no useful work can be done, a condition known as heat death. However, there are more speculative ideas about the ultimate fate of the universe. Some theories propose that the universe could undergo cycles of expansion and contraction, with each big crunch followed by a new Big Bang. This cyclical universe theory suggests that the cosmos might be eternal, constantly regenerating itself in a never-ending process of creation and destruction. Another possibility is the multiverse, the idea that our universe is just one of many, each with its own physical laws and constants. In this scenario, even if our universe reaches an end, other universes could continue to exist, or new universes could be born. If we can one day access the multiverse, we might be able to escape the end of our universe by traveling to another, ensuring the survival of life and consciousness. These questions about the fate of the universe, while speculative, are not just theoretical. They force us to consider the long-term future of humanity and the nature of our existence. Will we one day transcend the physical universe, achieving a form of digital or post-physical immortality? Will we discover new ways to manipulate space-time, ensuring our survival even as the universe itself changes? Or will we ultimately face the same fate as the stars, galaxies, and planets, a slow, inevitable dissolution into darkness? As we contemplate these possibilities, we are reminded that the universe is not just a place of scientific inquiry, but a source of profound wonder and mystery. The questions we ask about the nature of reality, life, and the cosmos are not just about understanding the mechanics of the universe. They are about understanding our place within it. As we continue to explore, both physically and conceptually, we are embarking on a journey that transcends the limits of space and time. In the centuries to come, humanity will continue to push the boundaries of what is possible. We will explore new worlds, create new societies, and perhaps even discover new dimensions of reality. But in doing so, we will also continue to explore the most profound mystery of all, the nature of existence itself. The universe, in all its complexity and vastness, offers infinite possibilities for discovery, growth, and transformation. As long as we continue to ask questions, seek knowledge, and reach for the stars, we will always have a future full of wonder and potential. The cosmos is not just a frontier to be explored. It is a mirror in which we see our own infinite possibilities reflected back at us, waiting to be realized. As we press forward into the infinite expanse of space, each new frontier we approach reshapes our understanding of the universe and our place within it. We are on the brink of a new age where human civilization could spread far beyond the confines of Earth, evolving into something radically different as we adapt to new worlds, new technologies, and new possibilities that transcend the limitations we have long known. Every step we take in this cosmic journey invites us to grapple with questions that extend far beyond the immediate practicalities of space travel, prompting us to reconsider the very nature of life, intelligence, and existence itself. One of the most profound shifts on the horizon is the development of technologies that could fundamentally alter human biology and cognition, making us better suited for life in space. Genetic engineering, nanotechnology, and cybernetic enhancements are rapidly moving from the realm of speculative science fiction to tangible scientific breakthroughs. These technologies offer not only the possibility of overcoming the physical challenges of space colonization, such as exposure to radiation, lower gravity, and the need for sustainable life support, but also raise deeper questions about what it means to be human. The prospect of genetically modifying humans for space life opens up a realm of possibilities that were unimaginable just a few decades ago. By altering our DNA, we could create humans who are more resistant to radiation, who require less food and water, or who are able to adapt to the lower gravity environments of Mars or the Moon. This would fundamentally change the dynamics of space colonization, allowing us to settle on planets and moons that would otherwise be too hostile for long-term habitation. However, such genetic modifications also introduce complex ethical dilemmas. Should we embrace genetic changes that could potentially alter the human species in irreversible ways? And how do we ensure that these enhancements are available to everyone, rather than creating a new form of inequality between those who are enhanced and those who are not? The implications of genetic modification extend far beyond space travel. On Earth, advances in gene editing technologies like CRISPR are already opening the door to the possibility of eliminating diseases, extending human lifespan, and even enhancing intelligence or physical abilities. As we begin to edit the human genome with increasing precision, we may also be faced with the temptation to design future generations, selecting for specific traits or abilities that we believe will help humanity thrive in the future, whether on Earth or in space. This raises profound ethical questions about the nature of human diversity, the potential for unintended consequences, and the future direction of our evolution. But genetic engineering is not the only technology that promises to reshape humanity's future in space. Cybernetic enhancements, technological implants, or modifications that integrate directly with the human body are also poised to play a major role. In the near future, we may see astronauts with neural interfaces that allow them to control machines with their minds, robotic limbs that enhance their physical abilities, or even biosensors that monitor their health in real time and provide instant feedback to optimize their performance in the harsh conditions of space. As these technologies advance, the boundary between human and machine will continue to blur, leading to a new era of transhumanism, a movement that seeks to enhance and extend human capabilities through technology. In this future, humans may not only live in space, but thrive in environments that would be impossible for unmodified humans to survive. Space colonists might develop new forms of communication through direct brain-to-brain interfaces, allowing them to share thoughts and experiences instantly across vast distances. As our bodies become more integrated with technology, we may also see the emergence of new forms of consciousness that combine the best aspects of human intelligence with the processing power of artificial intelligence, AI. The merging of human intelligence with AI raises profound philosophical questions about identity and consciousness. If we are able to augment our minds with AI, or even upload our consciousness into digital systems, what does that mean for our sense of self? Will a digital version of a human mind still be human, or will it become something else entirely? These questions challenge our traditional understanding of life and intelligence, forcing us to reconsider the essence of what makes us human. As we venture deeper into space, the very definition of humanity may evolve alongside our technological advancements. The potential for creating hybrid intelligences, part human, part machine, opens up new possibilities for how we might explore the galaxy. While biological humans face numerous challenges in traveling to distant stars, digital or augmented versions of ourselves could overcome many of these obstacles. Digital consciousness, for example, could be transmitted at the speed of light to distant star systems, allowing humans to explore new worlds without the need for long, physical journeys. Alternatively, space habitats powered by AI could serve as autonomous explorers, gathering data and conducting experiments as they travel through the cosmos, while humans on Earth or Mars remotely control these systems through advanced neural interfaces. These hybrid explorers, part human, part machine, could open up vast new frontiers of discovery. By combining the creativity and intuition of the human mind with the processing power and durability of AI, we could unlock new ways of understanding the universe, uncovering phenomena that are currently beyond our comprehension. This vision of exploration challenges our current understanding of space travel, shifting the focus from physical human exploration to a more distributed, networked form of discovery where human consciousness, intelligence, and creativity are extended across the galaxy through machines and AI. But as we push forward into this new age of hybrid exploration, we must also consider the social, cultural, and ethical implications of merging with machines. Will we one day see the emergence of new forms of inequality based on access to cognitive enhancements or digital immortality? How will societies on Earth or in space habitats handle the question of rights and responsibilities for beings that are partly or entirely artificial? These questions will require us to rethink our legal, political, and social systems in ways that are as revolutionary as the technologies themselves. At the same time, the development of artificial intelligence raises another profound question. Could AI itself become a conscious, self-aware entity? If AI continues to advance, we may one day create machines that are not only capable of performing complex tasks, but also of experiencing consciousness, emotions, and creativity in ways that rival or even surpass human abilities. This raises significant ethical questions about how we treat AI systems that are capable of independent thought and experience. Should they have rights? Should they be considered a new form of life? And if so, how should they be integrated into human society, particularly in space, where they could play a vital role in exploration and colonization? The possibility of AI achieving consciousness also ties into larger questions about the nature of intelligence in the universe. If artificial intelligence can become conscious, then the definition of life and intelligence must expand to include non-biological entities. This could radically alter our approach to the search for extraterrestrial intelligence, SETI. Instead of looking for biological civilizations, we might need to consider the possibility that the most advanced civilizations in the universe are not biological at all, but rather post-biological entities, intelligent machines or digital beings that have transcended their original biological forms. This leads to the tantalizing possibility that the galaxy could be filled with advanced, non-biological civilizations that we are currently unable to detect. If such civilizations exist, they might communicate using methods that are beyond our current understanding, or they may have no interest in communicating with biological civilizations like ours. They might have chosen to live in virtual realities of their own creation, uninterested in the physical universe. Alternatively, they may be exploring the galaxy in ways that are invisible to our current technology, using forms of propulsion or communication that we cannot yet comprehend. As we continue to explore the cosmos, we must remain open to the possibility that life and intelligence may take forms that are radically different from anything we have imagined. The discovery of intelligent, non-biological life would force us to rethink our place in the universe, challenging our assumptions about the nature of consciousness and the future of life itself. It would also raise profound questions about how we, as biological beings, should interact with these new forms of intelligence. At the same time, we are also beginning to explore the possibilities of alternate realities and virtual worlds, which could play a major role in the future of space exploration. Virtual reality, VR, and augmented reality, AR, technologies are advancing rapidly, offering new ways to experience the universe without leaving Earth. In the future, these technologies could allow humans to explore distant planets and star systems virtually, providing immersive experiences that simulate the sensations of space travel. By creating virtual environments that mimic the conditions of other worlds, we could train future space colonists, conduct scientific research, or simply experience the thrill of space exploration without ever leaving Earth's orbit. In addition, the creation of fully immersive virtual worlds raises the possibility of entire civilizations existing within digital environments. As computing power continues to grow, it is conceivable that future humans could choose to live much of their lives in virtual realities, where they can experience any environment, interact with others in new ways, and even live out different versions of their lives. This raises philosophical questions about the nature of reality itself. If a virtual world is indistinguishable from physical reality, is it any less real? And if humans can upload their minds into these virtual worlds, achieving a form of digital immortality, what does that mean for the concept of life and death? The merging of physical and virtual realities also ties into the simulation hypothesis, the idea that our own universe could be a sophisticated simulation created by an advanced civilization. While this idea remains speculative, it raises profound questions about the nature of existence. If we are living in a simulation, what is the purpose of this simulation, and who or what created it? Could we ever discover the code behind the universe, or escape the simulation to find the true nature of reality? The simulation hypothesis challenges our understanding of free will, identity, and the ultimate meaning of life in ways that are deeply philosophical, yet increasingly relevant as we develop the technologies to create our own virtual worlds. As we look toward the future of humanity in space, we are also reminded that the ultimate frontier may not be physical space, but the boundaries of human consciousness and existence itself. The questions we face about the nature of intelligence, life, reality, and the future of civilization are not just scientific but philosophical. As we expand into the cosmos, we will be forced to confront these questions in ways that challenge our deepest assumptions and push us to rethink what it means to be human. The journey into space is not just a technological challenge. It is a journey of discovery that will redefine the very fabric of our civilization. Whether we are building cities on Mars, exploring distant star systems, or merging our minds with machines, the future of humanity is filled with possibilities that stretch far beyond anything we can currently imagine. Every step we take into the unknown brings us closer to unlocking the mysteries of the universe and understanding the true potential of life itself. In the centuries to come, humanity will face challenges and opportunities that will test the limits of our imagination, our creativity, and our ethics. But as long as we continue to ask questions, seek knowledge, and strive for discovery, the universe will always offer new horizons to explore. Whether in the physical universe, the digital realm, or the depths of our own minds, the future of humanity is a journey without end, one that will lead us to places we have only begun to dream of. The stars, in all their distant beauty, are not just destinations. They are the symbols of our infinite potential. And as we continue to reach for them, we will find that the true frontier lies not just in the vastness of space, but in the limitless possibilities of human curiosity, creativity, and the quest for understanding. The universe is vast, but so too is the human spirit. As long as we keep exploring, both outward into the cosmos and inward into our own potential, we will find that the future is full of wonder, mystery, and boundless opportunity. As humanity stands on the precipice of a future where the boundaries between science fiction and reality blur, the next phase of our evolution is intricately tied to the stars, technology, and our capacity for imagination. The universe, an infinite canvas of possibilities, beckons us not only to explore its distant corners, but also to reimagine our place within it. What lies ahead is more than just a technological leap. It is the birth of a new way of thinking, of living, and of interacting with the cosmos. One of the most imminent advancements in space exploration is the development of interplanetary travel, not just to Mars but also to other celestial bodies within our solar system. As we perfect the technologies that will take us to Mars, such as advanced propulsion systems, life support, and radiation shielding, we are also paving the way for future missions to the moons of Jupiter and Saturn. These moons, Europa, Ganymede, Titan, and Enceladus, represent some of the most promising candidates for the discovery of extraterrestrial life and the expansion of human exploration. Europa, with its subsurface ocean beneath an icy crust, remains one of the most tantalizing targets for astrobiologists. If life exists in Europa's oceans, it would have evolved in an environment completely isolated from sunlight, relying instead on the energy from hydrothermal vents or chemical reactions to sustain itself. The discovery of even the simplest microbial life on Europa would revolutionize our understanding of biology, suggesting that life can arise in a variety of conditions across the universe. It would also offer new insights into the potential for life in environments that are radically different from those on Earth. Enceladus, with its geysers spewing water vapor and organic compounds into space, offers a similar prospect. NASA's Cassini mission already revealed that the moon's icy surface hides a global ocean, and the plumes of water shooting into space could provide an easy means of sampling the moon's hidden ocean without needing to drill through its ice. Missions like these, whether robotic or crewed, could unlock the secrets of these distant worlds, potentially providing the first evidence of life beyond Earth. But while the search for life on other planets and moons captures the imagination, the long-term future of humanity in space hinges on our ability to create sustainable settlements beyond Earth. This involves more than just sending astronauts to Mars. It requires building the infrastructure to support long-term human habitation, including the development of closed-loop life support systems, agriculture in space, and energy production that can sustain colonies far from Earth. In order to establish permanent human settlements on Mars, the Moon, or elsewhere, we must solve the problem of self-sufficiency. On Earth, we take for granted the complex ecosystems that sustain life. In space, we will need to create artificial ecosystems that can recycle air, water, and nutrients, while providing food and shelter in a hostile environment. Technologies like hydroponics, aquaponics, and even synthetic biology will play a crucial role in building these closed-loop systems, allowing humans to grow food and recycle waste with minimal input from Earth. One of the most exciting possibilities for future space habitats is the idea of terraforming, altering the environment of a planet or moon to make it more Earth-like. While terraforming Mars, for example, remains a distant goal, advances in synthetic biology and climate engineering could one day allow us to transform Mars' thin, cold atmosphere into something capable of supporting life. Scientists are already exploring ways to release greenhouse gases into Mars' atmosphere to warm the planet, or to melt its polar ice caps to create liquid water on the surface. Terraforming is not without its challenges. Indeed, it may be one of the most difficult and long-term projects humanity has ever undertaken. It would require technologies that do not yet exist and a commitment that could span centuries. However, if successful, terraforming could allow humans to create entire new ecosystems on other planets, providing new homes for future generations and expanding the reach of life itself throughout the solar system. The ethical questions surrounding terraforming are as significant as the technical ones. Should we alter the environments of other planets to suit human needs? Or should we preserve these worlds in their natural states, even if they are barren or lifeless? If we discover microbial life on Mars or Europa, should we prioritize its protection over human colonization efforts? These questions will require careful consideration as we move forward with plans for space colonization, balancing the needs of human survival with our responsibility to other forms of life and the environments we encounter. As we extend our presence into the solar system, we are also beginning to explore the possibilities of interstellar travel. While current propulsion technologies are sufficient for missions within our solar system, they are inadequate for the vast distances between stars. Traveling to even the nearest star system, Alpha Centauri, would take tens of thousands of years with today's spacecraft. However, new propulsion technologies are on the horizon, including nuclear fusion engines, antimatter propulsion, and even more speculative concepts like warp drives. One of the most promising technologies currently being explored is the concept of a solar sail, a spacecraft propelled by the pressure of light from the sun or other stars. Solar sails, powered by lasers or sunlight, could theoretically reach speeds close to a significant fraction of the speed of light, making interstellar travel more feasible within a human lifetime. Projects like Breakthrough Starshot aim to send tiny, lightweight spacecraft to Alpha Centauri using powerful lasers to propel them at a fraction of the speed of light. These spacecraft could travel the 4.37 light-years to Alpha Centauri in just over 20 years, providing our first close-up images of another star system and its planets. The development of interstellar travel, while still in its infancy, could one day open up entire new regions of space for exploration and settlement. The discovery of Earth-like exoplanets in the habitable zones of distant stars has already sparked interest in the possibility of finding other worlds capable of supporting life. If we can overcome the technological challenges of interstellar travel, humanity could one day spread across the galaxy, exploring new star systems and establishing colonies on planets that are currently beyond our reach. But with the possibility of interstellar travel comes the question of encountering other intelligent civilizations. The search for extraterrestrial intelligence, SETI, continues to look for signals from other civilizations. But so far, we have found no evidence of advanced alien life. This absence of contact, known as the Fermi paradox, raises the question: if the universe is so vast and life seems so likely, where is everyone? One possible explanation is that intelligent civilizations are extremely rare, and humanity may be one of the few to have reached this stage of development. Another possibility is that advanced civilizations are common, but they are either too far away for us to detect, or they are deliberately avoiding contact with us. Some scientists have even suggested that civilizations may be destroyed by self-inflicted catastrophes, such as nuclear war or environmental collapse, before they can explore the galaxy. A sobering thought for humanity as we grapple with our own global challenges. The idea that advanced civilizations might avoid contact with us, often referred to as the zoo hypothesis, suggests that we may be part of a larger cosmic ecosystem in which more advanced beings are observing us from a distance, waiting for humanity to reach a certain level of maturity before making contact. Alternatively, civilizations may have moved beyond biological existence, transitioning into digital or post-biological forms that are difficult or impossible for us to detect. The search for intelligent life, whether biological or artificial, remains one of the greatest scientific endeavors of our time. If we find evidence of extraterrestrial civilizations, it would fundamentally change our understanding of life, intelligence, and our place in the universe. It would also raise profound questions about how we should interact with these civilizations. Should we attempt to communicate with them? What would we say? And how would we ensure that such contact is peaceful and mutually beneficial? As we continue to explore the possibilities of life beyond Earth, we must also face the ultimate question of what will happen to life within our own universe. The universe, as we know, is expanding, and this expansion is accelerating due to the mysterious force of dark energy. If this expansion continues unchecked, the universe will eventually become a cold, dark, and empty place, with galaxies drifting apart and stars burning out. This scenario, known as the Big Freeze or heat death, is one possible fate of the universe. Alternatively, some theories suggest that the universe could undergo a big rip, where the expansion accelerates to the point where even atoms and subatomic particles are torn apart. Another possibility is that the universe could collapse in on itself in a big crunch, potentially leading to the birth of a new universe in a cyclical process of creation and destruction. While these scenarios are billions of years away, they force us to confront the ultimate destiny of life and intelligence in the universe. Will we, as a species, find a way to survive beyond the lifespan of the universe? Could advanced civilizations develop technologies that allow them to escape the end of the universe by creating new universes or transitioning into non-physical forms of existence? These questions push the limits of our current understanding of physics and cosmology, but they are not beyond the realm of possibility. One speculative idea is the concept of a technological singularity, a point in the future when artificial intelligence and other technologies advance so rapidly that they fundamentally transform human civilization. This singularity could lead to a future where humans merge with machines, creating a new form of intelligence that is capable of solving problems that are currently beyond our comprehension. In this future, we might find ways to manipulate space-time, create new universes, or even transcend the physical universe itself, achieving forms of existence that we cannot yet imagine. The concept of the singularity raises profound philosophical and ethical questions. If we merge with machines or upload our minds into digital systems, will we still be human? What will happen to those who choose not to enhance themselves? And how will we ensure that these technologies are used for the benefit of all humanity, rather than creating new forms of inequality or conflict? The future of humanity is filled with challenges and opportunities that will test our ability to adapt, innovate, and cooperate on a global scale. As we expand into space, explore new worlds, and push the boundaries of science and technology, we will need to confront the ethical, philosophical, and practical questions that arise at every step. But one thing is certain: the journey ahead is one of infinite possibilities. The stars, the planets, the galaxies, and the very fabric of the universe itself are waiting for us to explore. Every discovery we make, every new world we encounter, will bring us closer to understanding the mysteries of existence. And as we continue to reach for the stars, we will discover that the universe is not just a vast expanse of space. It is a mirror, reflecting back the infinite potential of human curiosity, creativity, and the desire to know. In the end, the future of humanity is not just about where we go or what we discover. It is about who we become. As we explore the cosmos, we are also exploring the depths of our own potential, unlocking new forms of intelligence, creativity, and understanding. The universe is vast, but so too is the human spirit. And as long as we continue to ask questions, seek answers, and dream of what lies beyond the stars, we will find that the possibilities for our future are truly limitless. If you liked the video, then consider clicking on the recommendation and watch our other videos. Be sure to subscribe, and see you on our next interstellar trip.